hit on the hour.
It's about that time.
So, hello, welcome back everybody for the fourth and final session of the Reddit Robotics Showcase. Thank you everyone who's been following along this weekend and participating. It's been an absolute pleasure. We're now on to our final category, which has been generously titled Human-Robot Interaction, but of course we do have kind of a loose fit theme. So while our keynote speaker is an esteemed and illustrious researcher within the field, you'll see all kinds of presentations today, and we've got a glove from Shadow Robotics, a great presentation on humanoids for general purpose applications, and a really cool example of robot art using a tentacle robot, a continuing arm like we saw earlier today. So with that in mind, I will hand over to our keynote speaker, Dr. Ruth Aylett.
Hi, well, great to be on this, and like any other researcher, delighted for an opportunity to talk to you about my field. So I'm going to talk about social agents and human-robot interaction. I'll explain first what I mean by social agents, because I had the impression that everyone might not have come across the term. Then I'll talk a little bit about expressive behavior, which is one way of making agents more social, and how we use theory from psychology to do this. And then I'll give an example of a socially competent robot we've been working on, with some example experiments that we've been carrying out, and then something about the architecture issues involved in producing a socially competent robot. Hopefully there'll be a reasonable mix here of technology and psychology, and that's inherent to this field. So don't come into this field if you hate psychology and just want to do the technology, because it's inescapable. You have to do both. So what is it that I'm talking about? Well, any agent, whether it's a robot or a graphically embodied character, and let me say that I talk about both of these, and to some extent I regard them as interchangeable. Both types of agent have to have some kind of task competence. That's to say they have to do a job and do it reasonably successfully. This is much easier for a graphically embodied character than it is for a robot. As we all know, if we work on robots in the real world, we have physics, things go wrong, connections fail, the robot is hard to control, and all the rest of it. So task competence is not always very easy to obtain. But building on task competence for a social agent, we need a bit more than that. So I'm going to talk briefly about role and social affordance, and I'll explain what I mean by social affordance. And then on top of that, we need some social interaction skills. And we need this because we're trying to make these agents work in normal human social environments. This is not a factory that's organized entirely around a robot or a robot line in most factories. This is not a laboratory, although we do experiments in those, in which we can control the environment and we can tell people exactly how they should be interacting. We're really talking about normal human social environments and whether we can fit our social agent into those environments in such a way as to be useful and pleasant to interact with. So that's a very demanding target. We don't have many current social agents that can do this, but I'll show you one that does. Affordances, I said I'd talk about those. Well, affordances comes from industrial design, actually. So here's, yes, you recognize that, door handle, yes? You know what to do with that. You know that you should press it down because the lever tells you this. Press me down, it's effectively saying. That's an affordance. We design objects so that it's easy to do with them what you want done with them. Now let's look at a different doorknob. This has different affordances. It's round. We know that we're supposed to turn that because it's round. It hasn't got a lever on it. That's its affordance. And we can see the little hole at the end, which is a keyhole. And we know that that's where you can put a key in order to lock or unlock the door. So the design tells us what we can do with those objects. Now, the same sort of thing applies to a social agent. Only in this case, I call it social affordance, because the form of the agent and its behavior really tells you what sort of interaction you can have with it. This operates at quite an unconscious level, the same way as doorknobs do. We don't stand there thinking, what do I do with this doorknob? The affordance is, if you like, intuitive. And the way we design social robots also indicates what sort of affordance socially we expect, what sort of interaction we expect. So here's a set of initial social robots. What do we do with these? Well, the affordance is aimed at children, you would say, looking at those designs. If you could see their size, you would notice they're also pretty small. So the biggest one, which is on the right, the now, is what, 0.5 meter tall, most, perhaps a little less. The affordance of these really is toys, would-be children, play, that kind of thing. So when you look at these, that's the message you're getting. We play with these. We do entertaining things with these. That's what they're for. Let's look at a different one. This is the Sony Abo. The social affordance here is pet. We look at that and we go, oh, that's a mechanical pet. That's a robot dog. Obviously, children as well may want to interact with it, but actually in Japan, a lot of adults have had these Abo dogs as pets. So this is the idea of a synthetic pet. And here I'm talking about a role as well as an affordance, aren't I? Just as I said toy in the first case, I'm saying pet, which is a role in the second case. Those are pretty obvious. It's less obvious what this one is for. This isn't actually the pepper, but it's another pepper-like design. Like the pepper, it has the form of, well, I tend to call them rather cynically over-helpful young women, which I don't think is a good affordance because it actually makes people think they can bully robots like that. And people do bully robots if they get a chance, I'm afraid. Everyone who has a robot knows that leaving it unattended in a public place is really not a very good idea. So what's this robot actually going to do? It's a bit of a mystery. The social affordance is much more opaque than the two previous sets of robots we looked at. What about this one? Now, this is the fur hat. It's a desktop robot. It's called a robot because its face moves. It has video projection inside. That makes it versatile from the point of view of animating the face, but it hasn't got any other means of interacting with the environment. Pretty clear that the affordance of this one is talk only. It's not going to move around. It's got a nice big mouth. Its eyes are looking at you. It's going to talk to you. It's going to interact through speech. So that's its affordance. Now we have a couple more examples where really functionality is dominant. You couldn't have said that for the previous ones. If I said to you exactly what is the function of those robots, you wouldn't really know. This one, I think, is pretty obvious. This was the Baxter Robot, no longer made. And looking at those great big arms and shoulders and the prongs on the end, you go, oh, yeah, this one is for picking things up. It's a two-armed manipulating robots. That's what that is. So the affordance is clear. I'm not sure its social affordance is so useful because looking at those great big arms, would you want to stand right next to it? It was intended to be a safe robot to stand next to, actually. The arms were designed to be compliant so that they wouldn't actually hurt you. But even so, the sight of it, I think, is pretty intimidating, even with its nice little groovy face on the tablet at the top there. So this affordance, social affordance, isn't really very social. It's dominated by, I'm going to do a job for you, and that's it, pretty much. And the same could be said of the Boston Dynamics Spot robot, I think. Another nice piece of engineering, incidentally. There's some great engineering in these robots. Not very autonomous, mostly. This one, well, people actually find it slightly creepy, in my experience, because it moves very like a dog, but it isn't quite a dog. And the snake-like gripper on the top doesn't really improve it. So what's its social affordance? Its social affordance is pretty much, I'm going to do something and will you steer clear while I do it, please, I think. So it's, again, very functionally dominated. So if you're doing social robots in particular, you've got to think carefully about the appearance, very carefully. There's yet more stuff, though, once you get your robot moving. So I bet you've never come across this word, most of you, and I'm not even sure how to pronounce it. I think it's Paraidolia. What is that, you might say? Oh, well, this is human tendency to see something in a random visual pattern and think it's meaningful, intended to be there. Often a face, sometimes a religious icon, cut an aubergine in half and there's the Virgin Mary in there, that kind of thing, okay? Humans see faces everywhere. We're hardwired to do it, that's why. The thing that a baby, when it's newborn, recognizes is something that looks like a face, and that's clearly a survival instinct. So you're not going to turn this off. People do see faces in everything. Here's a lovely set. I defy anyone not to look at that set of things, none of which are actually faces in the intentional sense, and not see some faces in there. You just can't help yourself doing it. Now, this is an important issue with social robots because it means that people are likely to see a face in the robot, even if you didn't think about it and didn't intend to animate it. And once you see a face, you expect a face to do something, particularly if the robot is something that moves, unlike most of the objects in there. I mean, the potato isn't going to move. We know that. Some of these things, I'm not sure what they are. The cone in the top left, which has a grumpy looking face. We know that's not going to move. We know that these are just visual possibilities. Once something starts moving, though, and it has something that looks like a face, that immediately triggers what is called our intentional stance. What's that, you might want to know? Well, Dennett, who's a well-known, philosopher of technology, said that what we do as humans is infer intentionality in things around us. It's another survival instinct, essentially. So if you're a fairly weak animal, as we were when we first came into the world, you need to know what the things around you are going to do, particularly if their intention is to eat you or attack you. So we're forever looking around us and trying to work out why things are going on. That's given us, gods of the rain and the storm, spirits of the trees and the lakes. Everything has intention. Everything is doing stuff. And in modern parlance, machines. I don't know if you've ever seen this one, but don't let your printer know you're in a hurry. They smell fear. I've had that problem. Paper jams when you least want them normally. Of course, we know that that's not true. It isn't malicious. It just feels like it. Once you get a robot that looks a little bit humanoid, that intentional stance, along with the Paraidolia, is going to kick in pretty hard. So we get anthropomorphism. And that means that if you're interacting with your human, if a robot is interacting with a human, the human is going to attribute human characteristics. This is a non-human object. Robots are not humans. They're machines, just like washing machines, only with different functionality from washing machines. So many of the human characteristics that this person is going to infer aren't actually there in the robot, but they're going to infer them anyway. I read one story where someone was doing a lifting task, a dropping and lifting task with a robot, said something to the robot, something like put it there, I think. The robot turned away immediately, ignoring the command, and the person thought they were being rude. The fact was their speech recognition system had failed and they hadn't managed to parse the remark. That was all. It was a function fail, which it usually is with robots. But for a human, that's intentional. They did it on purpose. So you have to be aware of this when you're doing social agents. On the side of human-robot interaction design, we do put human likeness into quite a lot of our robots. So there are also objective physical characteristics and traits that we try to put into the robot because we know the human expects them. In other words, we're trying to fulfill their expectations of how something like this might behave. It could be looking rather human, or it could be purposeful behavior, goal-driven behavior. Let me say that you don't have to look very human in order to trigger this anthropomorphism. But, and let's underline this fact, the more human you make your robot look, the stronger the assumption by the interaction partner that they're going to behave like a human. And since in the state of the art, robots do not behave like humans, only in very, very limited and flaky ways usually, they are going to be disappointed quite quickly. So my suggestion is that if you want to build a social robot, don't make it look too human. This is a rod for your back. He will simply generate high expectations and then you will fail to meet them. I'm going to give you an example of a successful social agent. There aren't many around in the robot field, but this is one of them. Now, the sound on this is in German, because this is footage taken in a German old people's home with the Paro seal robot, which you can see on the left of the screen. Paro seal robot is based on a Harper seal. It was produced by a Japanese researcher, very good researcher. He at first thought of cats as virtual pets, and then he realized that a robot cat was going to be far too difficult, not least its elegance of movement is unlikely to be replicated, never mind its behavior. And he realized that people don't interact with seals. So if the seal behavior isn't quite right, no one's going to notice. Also, it doesn't have parts sticking out very much that people can hurt themselves on or get their fingers trapped in. So a seal is a very nice object. And the idea of this seal is to give people with dementia in old people's homes more interaction than they're getting from people around them, because people around them get impatient with their limited interaction skills. So this woman actually, I don't think has dementia, but she is fairly immobile. And if you want to see the rest of this, it's from a video called Mechanical Love, which is not about sex robots, in fact. And it's quite an interesting section on this particular study of a robot in old people's home. So let's have a quick watch of this.
Ja, meinen Sie, ihr kennt die Stimme? Ja, weil der jetzt nicht mal umgekehrt ist. Ja, oder der hört einfach nur die Stimme. Ja, der hört auch, der nur hören. Ja, ich habe prima. Das macht nichts. Ruhig mal ein bisschen. Prima. Sehr schön. Das kann ich auch sagen. Oh, tschüss, das ist schön. Ja, also an und für sich ist es ja gewaltig, wie so ein Tier arbeiten kann, ne? Nur mit Strom. Ja, genau. Ne? Das ist ja eine Maschine wie eine Kaffeemaschine. Ja. Oder ein Toaster. Ja. Ihr kriegt Strom aus der Steckdose. Ja. Und da drin sind lauter Drähte und Batterien. Und so, aber wie lebendes Wesen. Genau, kommt einem so vor. Ne? Wie lebendes Wesen. Vor allen Dingen ist es für viele kranke Menschen. Ist das eine...
No, I don't mean to do that. So that has limited expressive behavior, but in fact, expressive behavior is what's drawing that user in. No real facial expression, though nice large eyes. It has glance, so it looks at the person it's interacting with. It has a little bit of gesture, it can wriggle, doesn't have hands and arms, and it has a certain amount of posture. It can move its head up and down, for example, or turn its head from side to side. And those are all things which are very important in human interaction. Now, what about emotion? So did that robot show emotion? It had very little face with which to show emotion. It was using voice more than face. It could, as I said, use glance. It could turn its head, and it could respond with those noises to the person interacting with it. What's interesting about the Paro, I think, is you saw in that video how deeply the woman is drawn into that social interaction with what's actually a very simple robot. It's not very complicated, just as well, really, given how fallible robots can be. But she believes it's an animal, even though we know it's not an animal, even though she's told it's just like a toaster or a coffee maker. She really believes in it as a social agent. The expressive behavior we can do with more human-like robots, with more expressive faces, draws on psychological theory, and that's what you see on this screen here. So Ekman was a psychologist, and he hypothesized a set of what he called primitive emotions, which he described as emotions which everybody recognizes across all cultures. So he came out with 6 of these. I'm sure if you're looking at these photos, you can make a guess at most of them, but let's put the labels on. So happiness, surprise, fear, sadness, anger, discussed. So it's not quite true that these are constant across cultures. In fact, people confuse anger and disgust quite readily. And other research has shown that in more collectivist cultures, for instance, in Asia, people tend to focus more on the eyes in these expressions. And in more individualistic cultures, like ours, for example, or in America, people tend to focus more on the mouth. So the interpretation of these expressions is not absolutely consistent across cultures in the way that Ekman suggested. I'll come back to some more problems with these primitive emotions in a minute. But let's say that we want our robot to be able to express at least these primitive emotions in order to engage with people. Why would we do that? Well, because it gives us some idea of what the robot's internal state is, and it engages us in some kind of affective interaction. It makes us feel the robot is responding to us in the way that robot voice in the Paro made that woman feel that it was responding to her and to her needs for companionship. So there's good reasons for giving our robot some kind of facial expression. How do we do this? Well, we can use something called the facial action coding system, which again, I'm not sure everyone knows about, so I'm going to explain it. So this is the idea that the face, the human face we're talking about here, has muscle groups that perform a visible expressive action. So it's not every single muscle on the face. This is groups of muscles that do something you might say that's expressively significant. And there are 44 of those, which is plenty. And there are more muscles than that. We've grouped some of them together. In this system, people give some of them names. There's the inner brow raiser, the cheek raiser, the dimpler, and so on. Some of the names are not quite as easy to parse as those are. The original use of this system, nothing to do with social agents at all. It was used to code expressions from video recordings of interaction. So people have videoed other people and are coding what their faces are doing as the interaction proceeds. And it's still used for this now. There are systems that will, to a certain extent, do this automatically for you. But it's been widely used generatively, particularly in social agents. It's been used for both graphical and robotic facial animation. Now I'm going to come back to the problem of robot facial animation in a second. In the graphical case, this, of course, is relatively easy to understand. We've got very human-looking faces. And this theory does apply to human faces. Animators apply it creatively to non-human faces. So if you're doing Donald Duck or Mickey Mouse, well, Donald Duck doesn't have a mouth, for instance. So it's not quite clear how some of those things would work. Never, how can Donald Duck have a dimple, for instance? No idea. But animators have found ways around this and apply them creatively to non-human faces. Here's some examples. So according to this system, this is how you do a smile. Action Unit 12. This is called I think the lip something. And what it does, it changes the nasolabial furrow. Oh, I do love that term. That's the bit around here, around your nose and mouth. There's a sort of triangle there, the infraorbital triangle. This bit is the furrow, and this bit is the triangle. And there's a change in the lip corners. So your lips go up, your nose sort of triangle changes its shape, and the furrow goes in a bit. That's what happens when you smile. Smiles are quite easy to recognize for this sort of reason. Not all smiles are happy smiles. I'll come back to this point in a minute. There's a thing called a Duchenne smile. I'll spare you why it's called that, but it's supposed to indicate actual happiness. And here the Action Unit 12 I just talked about, oh, it's called the lip corner puller, is also associated with an Action Unit 6, which is called the cheek raiser. And that means that not only your mouth moves, your cheeks move and your eyes move. As a result, your eyes will narrow. And that's associated with happiness. This is why if you really want to know whether people mean the smile they're smiling, you should look at their eyes and not at their mouth, because it's going to be a lot clearer from the eyes. So that's how we do facial action coding. And we can, of course, map this onto graphical faces quite easily, and robot faces, as we'll see, with a certain amount of difficulty. There are problems with this approach when used with the primitive emotions. It's easy to get from a primitive emotion to the expression. What's not clear, however, is whether the primitive emotions are actually that useful. In everyday interaction, you don't see many of those fixed expressions that I showed in those photographs. Very few of them, in fact. When we did an empathic robot tutor, we weren't interested in any of those expressions on a user's face. We were looking for boredom and frustration. So you could end up with a robot, if it does these primitive expressions, that is a bit over dramatic and is really going to freak people out because it's doing far too much with its robot face. There's another approach which can also be used to produce expressions that are not quite so dramatic or quite so fixed. And this is a system called Russell's Circumpolar model. What happened was that a guy called Russell back in the 80s went out with a load of cards with things written on them. This is called a card sort, another psychologist, and asked people to sort them into piles and then try to work out why people had put them in piles together or not together. And he came out with the idea that people were classifying the cards with these emotions written on them against two criteria. One was how excited or sleepy, we would say aroused, people actually were. So that's the vertical axis. And the other axis, the horizontal axis, was how pleasant over here or unpleasant the emotion actually felt. So in this high arousal negative emotion, you get things like frustration, anger, alarm, annoyed, distressed. You get excitement and ecstatic happiness and so on in the plus quadrant. Down here, where you've got good emotion, pleasant emotion, but not much arousal, you get satisfied, relaxed, calm. So pleasant, but not very exciting emotions. And over here, in the negative but calm sort of position, you get things like boredom, depression, sad, gloomy. So whereas the primitive emotions weren't very useful for our empathic robot tutor, you can see that at least we do have frustration and boredom on this particular version. So it's a more versatile model in some ways than the primitive emotions, though lots of people I know try to use the primitive emotions model in their social agents. We can map this circumplex model of affect onto faces. Yes, I've told you about the two components. It happened at some point, though, after Russell had come out with this, that people looked in this negative quadrant here and they said, hang on a minute, we've got angry there, and then we've got afraid almost next to it. Aren't anger and fear completely different emotions? And other people felt that they were. So they invented a third dimension called dominance. And the idea is that anger is in that quadrant but very dominant, and fear is in that quadrant but very undominant. The difference between aggression and retreat, you might say. This whole model is now called the PAD model for pleasure, arousal, and dominance. So we can, if we want, use it with the facial action coding system up to a point, or we can do something more direct. For instance, it's been shown that the brows, which are quite significant on human faces at least, can be significant on robot faces sometimes, is affected by both arousal and valence. So you get a lowered brow, which means the eyebrows go up for anger and high dominance, and you get a raised brow, which means they get flatter or curved in like this for sadness, which is low dominance. So what your eyebrows do is quite different in those emotions. Again, for positive valence, the eyebrows go up and get quite curvy, and for negative valence, they tend to flatten out. And that's just the eyebrows. I mean, I could give you more on this and facial features, but this is talk has a limited duration, so we won't do that. So we could drive facial features directly with valence and arousal if we wanted to as well. So that's an alternative psychological approach to doing this kind of thing. Both are used in social agents. Personally, I've never found the primitive emotions, as I said, particularly useful for the kinds of things I was doing. There might be application domains in which they are useful, but mostly short of a very short demo where big actions are going to engage people. If you want something that's going to interact for weeks at a time with people, as we would like our social agents to do in normal human social environments, something that's a little bit less overwhelming is probably a better idea. Now, this is the robot I've been working with recently. That doesn't look very human, does it? So here I am telling you all these psychological theories and how we manipulate bits on the human face, and then I show you a robot, and that face doesn't look terribly human. It is a bit human-like. It's a very ingenious, in my view, design. It's got 3 plates. It's quite easy to drive as a result. There's no actual mouth, but you can move the plates up and down. So the mouth can move up and down, although it can't change shape. The eyes are cameras and we can direct gaze, and these eyelids can go up and down as well. And this plate at the top can also go up and down, and then the neck can bend. So you can actually get a lot of expressive behavior out of that head, which is human-like, even though it's not a very human face. You might say, what's the social affordance? Well, you should be asking, what's the social affordance of that particular head? Well, in my view, the social affordance of it is cheeky chappy. It's based on principles of animation rather than real life. So it's taken, if you like, from comics rather than from naturalistic, human-looking interaction. And that's an advantage in that expectations are not going to be unduly raised, I would say. It's bound to be a bit cartoony in the way it operates, and it's bound to be fairly schematic. It's not easy to be subtle with a face like that. However, the more subtle your face is, the more you're going to find that if you put facial expressions on it and they're not right for the context you're in, the worse people are going to like it. So this at least has the advantage of not being too difficult to get into an appropriate state in a context. So is all this stuff I just told you at all useful for a robot face like that? And let's say some robots have even less face than this one does. That's what it looks like inside. It's got 11 degrees of freedom. Remember I said the human face has 44 muscle groups? Clearly, if we want to use the facial action coding system, we're going to have to somehow map the different facial action units onto the 11 degrees of freedom that we have got in order to do something sensible. So the next slide is one you're not really intended to read. It's just intended to show you how industrious we were in doing this. This is part of a huge table that we constructed, where down the left-hand side, we've got the particular degrees of freedom of the robot. The next column tells you which action units can actually be operated with that degree of freedom. So which action units of the 44 can we actually get up to 46 with winks and blinks, and 54 with necks and heads up and heads down. So which action units can we actually do with that one? Obviously, we can't do the lip corner puller, for instance, because we don't have movable lips. And then we've got here some ideas from that PAD model about what PAD says about how the degrees of freedom should be manipulated. And then further along the table, we read a lot of papers to see how people had done this kind of thing with their robots, and we drew conclusions. So I'm going to talk a little bit about the experiment in a minute, but initially, oh yes, I'm going to talk about that now. So what were we using this robot for? I'm going to show you the project video. Basically, we were interested in using our robot to see if we could help high-functioning adults with autism to improve their ability to recognize social signals, which are facial expressions quite often, not always, but quite often. So I'll now play the video, which I think is self-explanatory rather than tell you about it.
you. Today you are going to offer me some breakfast. Hi there. Sorry to disturb you. Could you open the Word tab on the desktop, please? Thank you.
Okay, so that was the project. We were trying to help adults with high functioning autism. The robot in the last section was running autonomously, and I had to cut it because it was running very slowly. This is just one of the interesting issues when you use a large robot. Having them navigate quickly is a bad idea because they're not that accurate, and you don't want them to crash into things or to people. But it's not much fun to watch on a video either. So that's one example of a social use of a social robot and the expressions that we were generating. Let's just make an important point here, though. I talked about emotions when I was talking about Ekman and the facial coding system. But most of the time, what people are using their face for is actually social signals. So emotion communicates internal state and it motivates actions. So if someone looks furiously angry and then swings an arm at us, we know that they're angry and we think that their anger is making them try to hit us one. Social signals have what we call interactional semantics. That just means they mean something when we're interacting with people. They can regulate our interaction. So there's turn taking. When we speak to someone, we say something, they say something. There's what's called back channel. So when someone's talking to you, you go, yes, okay, yeah, oh, right, that kind of thing. That's all back channel. Then they know that you're listening, basically. If you just sat there with your immobile face, they think, have they gone to sleep? Are they actually taking any notice of what I'm saying? They're communicative. So you might say they're acts of not speech. So approval and disapproval, which is what we were using in that experiment, are actual social signals. In other words, do I approve, or does the robot approve of the item it's being offered for its hypothetical breakfast, or does it disapprove of the item? Does it like it or does it not like it? So that's not a specific emotion, that's a social signal in the context of that particular interaction. And indeed, it's probable that because we were offering items to eat, there was too much weight on the open mouth signal, like that we're able to do quite easily because it looks like you want to eat something. Didn't think of that when we designed the experiment, of course. In the same way, some of these social signals didn't work properly. So we had a blink and a head turn, which entirely failed. It was intended to be approval. But in fact, because of the head moving sideways, people took it as a no in context and decided it was disapproval. So these things are simultaneous and overlapping. We manage this well in human-human communication. It's much harder to generate it in robot-human communication. So the meaning of a smile. Remember I said we can recognize smiles very easily? We can, but we don't know what the smile means unless we look at the context in which it's being made. So I said a Duchenne smile indicates happiness. It may indicate happiness, or it may not. What are you happy about? It could be a sort of sarcastic happiness. Someone's just said something foolish and you go, yeah, that was funny. but it doesn't mean you're happy necessarily. Culturally specific, in Asian cultures, smiles very often indicate embarrassment and not pleasure at all. There's the angry smile, there's the hello, I'm glad to meet you smile, there's the oh yeah smile, there's all sorts of smiles. It's the most ambiguous expression on a face, socially speaking. So the fact we can recognize it doesn't necessarily, as a smile, doesn't necessarily help us to know what it means. And generating it, we have to have some idea what we want it to mean in that particular context, which is not easy to determine at all. Incidentally, if you have companies coming in telling you that they can recognize human emotions, can I just assert quite emphatically that what I've just said means there is no one-to-one mapping between a facial expression and an internal emotion. It just isn't. Facial expressions are ambiguous and more likely to be social signals than direct expressions of emotion. That doesn't make it easier for us to generate correct expressions. Now you see why I said having a very human face is probably a bad idea, because getting all that right subtly with a human sophistication is very likely to go wrong. With a cartoony face, you're much more likely to get it right, or at least make it plausible. You're giving yourself some rope, not to hang yourself with in this case, but to give you some leeway in the interpretation. The user can supply the sophistication. Those were our expressions. Those were the 4 that you saw demonstrated. The top 4 were approval. The bottom 4 were disapproval. There's that wink head left, which didn't work. In fact, this is how they worked. The 4 ones on the left here, the approval ones. I'm trying to remember which was which is the wink. I think that's the wink. Yeah, so the green bit it was wrong. It was interpreted wrongly. The pink bit, it was interpreted rightly. So you can see that expression, the leftmost one and the rightmost one of the first 4, were very highly correctly interpreted. That is, as we'd intended them to be interpreted, as expressions of approval. The other 2 were not, and the wink was nearly always wrong. People misinterpreted that all the time. Sorry, the turquoise is negative, the pink is positive. That's what I mean to say. Over here, you can see that recognizing negative expressions was on the whole more reliable. 3 of them were recognized quite reliably as negative expressions. The leftmost one here, not so much. It was ambiguous how people recognized it. So you have to do this if you want to put expressions on a robot face, in my view. You have to test it out, and you have to test it out in specific contexts if you want your expressions to be correctly interpreted as social signals. This was us trying to see if the autism quotient, this is not diagnosed as autistic, but how many autistic traits you have. Many of us have these traits. We hoped that we would find that people who had higher numbers of traits of autism would find the expressions more difficult to recognize. That wasn't what happened. This scatter diagram shows correct interpretation of positive expressions and of negative expressions, generally across the whole spectrum. We don't exactly know why. We did find that the culture of the person, the home culture, had an effect. That goes back to what I said about expressions not being culturally independent, in fact. So we think that people from non-British cultures, other countries, this would be overseas students, in fact, were looking at the eyes, which in the case of this robot's not a good indicator of expression because its eyes don't change shape. So you really have to look more at the mouth on that particular robot. So it's culturally specific to people who look at mouths, you might say, that particular robot. Generating expressive behavior. How do we do it? Okay, so last bit of the talk, I'll try to be rapid here. It's all very well having these expressions on the face of your robot, but how are you actually going to know what expressions you should be generating in what context? Again, we go back to psychology, and what many of us have done is picked up a theory called cognitive appraisal theory, which says that events, actions, and objects are appraised in relation to your goals. In other words, what's in it for me is a driving point of interpretation and interaction. And this generates an emotion. When things are going according to what you would like them to go, you feel positive. When they don't, you feel negative. That's the basic idea. And again, you've got valence and arousal here. Oops, was interesting, wasn't it? You can implement appraisals with domain-specific rules, and you really have to do it in specific domains. The probability of impact on an agent's goals, and this produces what's called coping behavior. So here's a diagram to explain this. In this diagram, you can see external events top left, you can see the appraisal process in the middle, you can see the goals and so on the right-hand side. So, sorry, appraisal is mediating between external events and goals, generates an emotion. This goes into this coping box. What does that do? It's got two exits. One is problem focused, one is emotion focused. Here's an example. You're walking down the street and someone you don't know comes up and starts shouting at you. You're going to feel emotion. This impacts your goals negatively. You will be either scared or angry or both. What coping would you do? Well, the problem-focused coping, this is change things in the world, would be, if you were really angry, would be to hit the person or shout back, maybe, if you were less aggressive. Or if you were the fearful dominant person, you would run away quite fast. On the other hand, the emotion-focused outlet of this process says, oh, let's look at that emotion and see if we can deal with the emotion rather than actually hitting someone. So in this case, the coping process might say something like, I don't know this person. I've done nothing to annoy them. They're clearly crazy. Let's just ignore them and walk on. In other words, you would control the fear and anger, and you wouldn't let the fear and anger actually drive your action. So you can implement this kind of thing in a social agent. We have done this. Again, a slide that you're not supposed to look at, really. This is the Fatima Architecture. It's a cognitive appraisal architecture that we've developed for about 20 years now, I think. You can get it on GitHub at that address. It's now in a toolkit form. Easier to run on graphical characters than on robots in the toolkit form, but essentially an implementation of the previous diagram. So here's the sensor bit coming in. Here's the appraisal bit I talked about. Here's the emotional state being generated. We add knowledge about the world and how things work, because we always use this in order to work out what's happening and why it affects us. Out here, we've got actions in the world. And down here, we have two ways of doing the coping. One is to plan, and the other is to react. So that's just an implementation of what I told you in computer terminology. We have actually implemented this on a robot. We had ran a project called Lyric, which finished in 2016, where we looked at long-term companion robots. And that's, again, a diagram you're not going to take in the time you see it, but essentially it's a robot-based implementation. Being a robot, there's the Fatima box top right. All that stuff I showed you in the last diagram is in that box. But being a robot, of course, you have to sit it on a load more stuff. So we put in a mediating thing, which would map the stuff coming out of Fatima down onto robot competencies. If you've ever used ROS, Robot Operating System, then you can think of these as being ROS packets, probably. We also had a blackboard so that we could keep track of what was actually going on while we were doing this. And then a load of competencies for sensing and actuation, which every robot has to have if it's going to do anything sensible. So though it's not straightforward to implement this architecture on a robot compared to a graphical character, where you can just stick it into Unity or something like that, in fact, you can implement it on a robot, and then you get this architecture which allows you to generate the expressive behavior in a sensible sort of way. Okay, you'll be relieved to hear I got to the end now. So in conclusion, social agents work in demanding social environments, or try to, and they need social skills and social interaction behavior in order to do this. We can use theories from psychology to create these social skills and social interaction behaviors, both with expressiveness, the actual facial expression, and I could have talked about gesture as well, but I haven't, and with actually giving us an architecture which knows when to generate those things as well. But task competence, remember, there was the first thing in my first diagram, is still vital. And task competence is still very, very difficult in robots. Most robots are incompetent unless you put them in very tight environments. And so the problem with social robots is actually we can produce some socially relevant behavior in the human environment, but the task competence usually falls well short. And that's standard things like manipulating things the way people do, recognizing objects, recognizing faces, not hitting the furniture or hitting the person, running out of battery at a crucial moment. Actually, that's a major constraint on those social robots. That's why the Paro worked, because the Paro didn't try to do anything too complicated. It sits there, it doesn't walk around, it wriggles, it squeaks, it has a human, not a very human face, it can look at glance, it can react to voice. In terms of functionality, it doesn't have very much, but it works in terms of companionship and is shown clinically to work with in terms of companionship with people with Alzheimer's who are not getting enough interaction stimulation from the humans around them. So that was a very good set of design decisions. And if you want to do a social robot, you've got to think like that. Task competence has to be there, and hence the short life of social robot companies so far. It's a sad but absolutely undeniable fact that most social robot companies go bust. And that's because they don't have task competence. They just have nice social skills. Not enough. Okay, you want to read more about this? I'm an author, along with a colleague, of Living with Robots, What Every Anxious Human Needs to Know. Lots about social robots in there. So thanks for your attention. And if there are any questions, happy to answer.
That was absolutely fascinating. One of the comments here I'm reading now is, I wish I could take this as a class, and I agree. That felt like, I've learned a little bit about human robots, but that you put into words the way I've always felt around the Baxter robots, and I've been around them, and I really like Baxter robots on paper. It's a great idea, and everything should have worked out for that company. But when you're standing around it, even with the screen and the eyes that are meant to look where it's gesturing, just by the presence of it being so big and bulky, it makes you want to give it more space.
That's like scary.
Collaborate alongside you. Again, comments to say, absolutely amazing presentation. Thank you. That really gives a very insightful look into what it means to make robots that, as you point out, robots that are, when compared to humans, not considered incompetent. And that, really represents the challenge with social robots, that for all the things that we think about as technical challenges, when you put them alongside a human, it just doesn't stack up yet. And yes, the challenges of social robot companies. Fantastic. Michael, thoughts?
Yeah, no, I just wanted to say, I loved the robot that was part of your study, just because it's very impressive to capture, all the levels of emotion and kind of as few degrees of freedom as possible, right? Kind of that optimization problem that's hard to put a number on, but it's very impressive that it was able to be expressive while having, a fraction of the degrees of freedom as a human face, right? So we have a few questions from the YouTube stream. Our first one is, going back to the idea kind of at the beginning of your presentation, talking about, the purpose of a robot should be kind of self-evident in its construction. Well, how does that apply to more general purpose robots? If they're trying to accomplish a lot of different goals, how can you still make those goals self-evident in their construction?
Well, I think the point I would make here is that robots, multitask robots, fail. Okay, that's the problem with them. You give a robot too many things to do, it's going to be incompetent at nearly all of them. If you give a robot a few things to do, it's more likely to be successful. That's a sad fact. General purpose robot, no, run, do not walk, run away. Your general purpose robot will almost certainly fail. Yeah, robots are not up to it. Not in terms of task competence and sensing and manipulation or anything. So don't try to build general purpose robots. Yeah, that's my answer to that question. Don't do it. Okay.
Fair enough. How much of a concern
say that we'll hear the other side of the story from our next presentation, which is
but they're trying to do generalized grasp, I think, probably.
Yes.
Yeah, and that's an unsolved problem. And the problem with generalized grasp, that's one of the competencies I'd love to see on a mobile robot, because one of the major obstacles to functional task achievement on mobile robots is not being able to pick things up. Unfortunately, once you put an arm on a mobile robot, you've got a set of extra problems. One is you're drawing a lot more battery power. Okay. The next thing is you're putting a lot more weight on the top of the robot so you can reduce its stability. The next one is generalized grasping has itself got what? Well, the human hand itself, just the hand, has 22 degrees of freedom. Okay. Yes, you can do it, but you don't know where one end of the arm is either, because what's the position of the mobile robot? Okay. So how are you going to pick things up when you're not sure where the robot is, you're not sure where the base of the arm is, but you've got something in front of you need to pick up, and you can't do it in coordinate space. So essentially you need a reactive visual driven system to actually get your hand around the object. And that's apart from deciding how to pick it up. Is it a mug with liquid in it, which cannot be tilted? Is it very heavy, which we would normally assume so I'd love someone to produce functional arms. Our robot has arms, but they're not functional. They work well for gestures. The Baxter has very functional arms. So yeah, as you see, a very functional arm is not something you want to stand very close to. So this is a hideous problem at the moment, grasping for mobile robots. An absolutely hideous problem. I'd love for the shadow hands to be on a robot and to work well, but we're a long way from that yet.
Yeah, no, I agree. It's just a very complex problem, but it's great to see so much work going into solving it.
Oh, absolutely. As I said, many of us are waiting for somebody to succeed. It's a specialist field. It's not one that you're generally going to go into as a social robotics person. But absolutely. Yeah, we're waiting for people to solve this problem with bated breath, because it would make life so much easier for us if we could.
Yeah.
A couple more questions from the comments. In relation to the study with people with high functioning autism, did you find that the adults could then transfer their learned emotional recognition techniques to humans? What they were learning from the sessions, were they able to take that out of the lab conditions with them?
That's a very good question, but I can't answer it for two reasons. Okay. Well, three reasons. The first reason is that the pandemic cut across the project. So you cannot do human-robot interaction when you've got a lockdown, because you can't put the human and the robot in the same place. Okay. So we didn't get as far as the experiments that would have shown that. That's one reason. The second reason is that we decided halfway through the project, having engaged much more with high-functioning adults with autism, that actually we shouldn't necessarily have had that as our aim. That's an unfortunate thing when you're doing research. You start with a good idea, and then partway through you think, maybe that wasn't such a good idea. Okay, so the modern view on neurotypical versus non-neurotypical people would be that people should adapt to people who are not neurotypical, not force them to do all the adaptation. I mean, it's at the moment, as my slides show, 16% of people with diagnosed autism, even though they are high functioning and perfectly capable, only 16% are employed. It's very hideously high rates of unemployment. A lot of it's down to social signal processing. Things go wrong, people don't necessarily notice, and so on. But why should they have to do all the adaptation? Think of it as a cultural difference. Yeah, in culture, we say multicultural societies require adaptation on all sides and tolerance. And yet we're telling people with autism that we can't adapt to them and we shouldn't be tolerant of their behavior. They've got to change their behavior. So that's the second and most important reason. We came around to thinking that maybe we shouldn't have done this, and that probably what we should do is use this system to train managers to deal better with their employees who are high functioning with autism, instead of making all the wrong conclusions about them because they're unfamiliar with their behavior. So give me some money and we'll do the second project, and we'll use this to train managers instead.
Really,
sounds like a plan.
Yeah, again, a really interesting perspective on it. Yeah, to think that, I mean, obviously, I think most people here would say yes, we should be doing a lot more to accommodate these people. And I also think, particularly in the industry of robotics and science and technology, we all you can look around the room and say, yeah, a fair few of us are undiagnosed here, and there's nothing wrong with that.
Well, and also are high on autistic traits. So as I said, It's a spectrum, in fact. So you may be high on autistic traits without necessarily having been diagnosed or necessarily be diagnosable. Yes, and engineering and robotics and computing attract people who are higher on autistic traits because they have to do less human interaction, and that can be more stressful for them.
Gosh, enlightening that. Thank you.
Yeah.
Yes, well, that takes us to our time then, and we'll move on to the next presentation. But Ruth, thank you very much for your time and for giving this really fantastic presentation on a topic and really breaking it down for us.
Well, pleasure is all mine. Thanks for inviting me.
Very,
Thank you so
very
much for your
pleasure.
time. It's been really wonderful having you.
With that, then we will move over to very much in contrast, but still in the same thing, to working towards developing humanoids for general purpose applications by Nathan Boyd. So Nathan, if you're ready, we'll hand over to you.
Yeah, I should be able to. I'll share screen. All right, you guys can hear and see fine?
Wonderful.
Yep, we got you.
Awesome, cool. Yeah, so my name is Nathan Boyd. I work at a company called Apptronic. We're out in Austin. I'm also one of the moderators out here for Discord and for a lot of the other Reddit showcases. So I've been pretty involved with the overall process for everything here. But I wanted to do a presentation to talk about robots for the unstructured world and how exactly we're kind of trying to tackle this and look at this, bringing this research problem into something more practical that people can actually monetize and use for their everyday application. So just a little bit about me. My background has really kind of been all over the place. I've been anywhere from manipulation to drones and mobile robots, autonomous cars, and of course legged robots, getting things to do dynamic motions or building and assembling things in the real world. So I've really kind of hit all these different spectrums of the robotics world and trying to make things work in the real world. Many of these are well-known systems, and so being able to actually work with this hardware or build it from scratch even in both the open source world and in the professional world has been an absolute joy for me. But it's really a new world once you start to talk about something that's generalizable. And like we heard from the last talk, building something that's really generalizable is quite difficult. You want things to be utilitarian, you want it to have versatile autonomy, and you want to try to have as minimal infrastructure changes as possible for a lot of these real world tasks out there. So if you talk about applications like construction or things that are not easily in a structured environment, like in a warehouse, or even if it is a warehouse, it may be really expensive to do a change. Then you can start making arguments for a lot of actually general purpose robots that can do a lot of different tasks or multiple tasks instead of just one robot that does one thing. So this is kind of the context that we're thinking about here at Apptronic, and we've done a couple different products in order to generalize, in order to show this. So there are two parts of this coin. In this case, we're doing a lot of work with interaction and actuation. And then of course, that's more on the hardware side. The other side is control, and how do you actually build a control stack that is safe to work around humans and not going to break anyone's legs or break anyone's arm if you're in close contact with it, but still be very functional and robust to the real world. So to kind of kick off, I want to start talking about the hardware, what we are kind of developing in-house, what we've done in the past, and how it's kind of building up to what we're doing now, which is more humanoids work going into the future. So for the people who are familiar with hardware, this probably won't be too new for you, but for people who haven't really heard a lot about hardware, one of the more basic compliant motors that you can get out there is something called a series elastic actuator. This is something where you essentially have a motor, a gearbox, and then a spring on the end of it. And the point of the spring is that because you have such a high gear ratio, it's not that back drivable. So you need something in order to be compliant with the real world, in order to absorb that energy if you make an impact with it, because we don't want to be sharing gears. And the whole point of the series elastic actuator is that you can show high fidelity force control and have really good torque to mass ratio or torque to volume ratios without having any type of other issues like shearing gears. In addition, you also get low impedance rendering, which is essentially a measure of kind of this stiffness that you're getting inside the gear, in order that if you whack into something, you are not going to break the thing. You're going to be compliant and not rigid with the rest of the world. So this is like kind of your bread and butter. And you see this with a lot of cobot arms. So if you buy a KUKA arm or a UR arm or any of those kind of cobot arms, this is what's basically on the internals of all of them. But it's only one of many different strategies that you can really do for actuation out there. And while I'm only going to go through a couple of them, we're going to kind of see what each of the pros and cons are for each of them. So the other one is a parallel elastic actuator. So rather than being in series, you have a spring in series, you have a spring in parallel. You can think of this as a natural form of gravity compensation for a lot of robot arms, which makes robots very energy efficient. So you can naturally say, okay, the weight of this arm essentially means nothing because the spring is going to be compensating for all of that. And so this gives you a wide range of impedance rendering. So you can actually handle a wide variety of tasks, get a wide variety of stiffnesses and compliances, because your robot dynamics don't really matter as much because they're all being compensated for and it's all fed forward. And you can still get really good torque to mass because you have a large gear ratio that's actually actuating your arm. The last one that we're going to be talking about is essentially what we call quasi-direct actuation. If anyone's been following the legged world, this is a very popular form of actuation where essentially you have very low gear ratio and no mechanical spring in there. So it's less mechanically complex, but because you have a low gear ratio, you can have high bandwidth and very backdrivable system, which means that in your controls, when you're running your algorithms for motor control at a low level, you can add a virtual spring component. You can do digital impedance controls in order to make sure that you're compliant with the rest of the world. And this saves a lot on cost, and you're still able to keep a lot of the performance in your system. And these scale wonderfully. You can actually go up to fairly large radius gears or large radius motors with somewhat large gears in order to actually get large torque outputs from a system. It's really just kind of managing heat and a couple other different factors. So combining these three together, we've kind of shown a couple different products at Apptronic to show these different kind of competencies, and then we're using many of these different strategies in order to build our final humanoids. So kind of starting off, you want to look at the upper body platform as a humanoid. So before even looking at the complexities of a legged system, how would you even just do manipulation, and what are kind of strategies we can look at there? So for that, we had one of our first projects, which was Astro. And we're showing this for a lot of VR applications and telepresence applications, where we want a human operator to be able to directly control the upper body, but still be compliant with the rest of the world. So if you're going to have a lot of error in a VR context of from trying to control with your hands. And so you want a high amount of impedance in your system in order to make sure that you are not going to actually break anything when you run into it on accident or when you're trying to grasp an object. So we can see that even for just a small platform, the robot actually is quite fast and is able to move through a wide range of motions. It's a very human operating range that you can actually work in with the system. So you can do a lot of kinematic singularity, straight arms, and dealing with straight arms or other types of joint configurations that are nice for being able to lift objects around in the world and minimize the amount of torque while not being unstable from a control standpoint. And like I said, we can do this with VR. Ooh, what's going on here? So here you can see an application where one of our engineers is sitting in the background here using just some open VR headsets and controllers in order to control the robot. And we're able to do end effector tracking or torso tracking, so you can get your whole body to bend over and pick up a box or to do a different manipulation task. In addition, because these VR hand sticks are a fair amount of buttons and tactile sensing on them, you can start to use those buttons in order to actually get pretty nice finger control and be able to grasp objects on the fly. So our kind of ad hoc solution to saying if we can't really do it autonomously and it's too difficult to grasp autonomously, then even in these really remote cases where, say, you're out in an oil rig and you need to put a robot out there to just pull a lever to open a door or to do a very fine manipulation task, you can always just VR in, or you can always do a remote operation, just have an actual human control it. And that can still save you a lot of money and not have to fly someone out to an oil rig, for example. So the next robot that we were looking at is Scorpio. So this was a mobile manipulator where we were looking at really trying to lower the mass of the robot as much as physically possible while still keeping really high payloads. So this uses parallel elastic strategies. So it's really hard to get a robot to actually be a 1-to-1 payload to mass ratio, but what we're actually seeing with Scorpio is that we can even exceed what humans are doing in terms of their actual mass, and able to have an insanely light robot that can still lift well over 10 kilograms worth of payload weight. And so you can see the robot's still extremely compliant and extremely lightweight. You can see this is Nick here, kind of just working with the suction gripper and moving it around with his hands. It really, because of all that natural spring compensation, it just floats around like a butterfly. And if you want to be able to move something on your own, it's extremely easy to work with. It's also quite repeatable. So like I said, no worries about the robot dynamics, means that the system's pretty repeatable and we can do pick and place tasks quite easily with this. So here you can see just some depalletization types of contexts where the robot can pick up a box and do a repeatable pick and place task. So you can see we'll do this many times and we can go up to the heavy payloads as well. So this is 15 pounds, almost 10 kilos, and we're able to still lift it just fine. So while this isn't shown on a mobile robot, it's very applicable to a mobile robot. So if you wanted to throw this onto like a Husky or something like that, it's provided that your center of mass is fine enough and won't tip over, then you can actually do some pretty great things with this arm. But obviously this isn't really the full frontier of things and getting general purpose. For us in the human world, we design a lot of the human environment to basically our specifications. So we have a lot of things like doors, staircases that are in our human environment that are actually really difficult for robots to get through. And that can straight up just make or break the case for a robot to actually be used for an application. Because if they have to go between 2 points like A and B, if it's a mobile robot and has no way to actually get through a door, then you can actually just entirely remove that product from being an option for the robot. So things like doors, stairs, or unstructured terrain are a big issue from a manipulation and a locomotion perspective in the industry. So when we're looking at kind of intelligence for legged robots and where we're really going with it. So we kind of talked a lot about actuation and sensing already, what the different motor platforms are. You have to also start talking a lot about coordination and state estimation. How does the robot balance in the world? How do we make sure it doesn't fall? Because those are very safety critical things. You don't want to have a 150-pound robot just suddenly tipping over and falling on top of you, or doing something really scary and fast because its foot slipped and it now freaks out because it can't find the ground. The next one is motion control. So kind of building off of that, just how do you balance? How do you really start to plan these more agile maneuvers where you don't want to be in contact with yourself? You don't want to trip over your own legs, and you want to kind of plan these more dynamic motions. Or if you're picking up like a box, for example, you want to make sure that you are using your entire body in that motion, and you're not just simply only lifting with like just your arms or just your back, for example. You don't want to focus on just one motor. You want to try and use a whole body manipulation. Then once you have that motion control, you can start talking about perception. So this is adding feedback into the loop from perception system, telling you where you want to put your foot, for example, or where you might want to grasp the world, and put a point of contact to stabilize the robot. So this is what you see a lot with like autonomous cars and using LiDAR sensors and camera sensors in order to actually step over wood blocks or unstructured terrains and having that feedback into the system. And then continuing up this hierarchy, you get to the planning layer. So now that we can see the ground and we know where the ground is and we can balance fine, we can start sending high-level references to the robot, where if we say, hey, you know, walk forward down this hallway, and then maybe there's a lower level controller that's telling you to avoid obstacles in the way. That's when you get to the planning layer of hierarchy. And this is now when we're starting to really call the robot a lot more autonomous, when it's doing a lot of its own decision making and trying to go from A to B in the world and avoid obstacles or navigate crowds. And then the highest level would be decision autonomy. In academia, we would call this task planning for a lot of it, or task and motion planning if you're combining it to the lower level planning. And this is where we start thinking about symbolic reasoning, orders of tasks, where you say, I want to pick up object 1 and then object 2, and then go complete task 3 with object 1 or something like that. And kind of come with these symbolic plans that are traditionally very difficult for continuous motion planners to actually solve for. So if you are out there in the open source world, you can actually get the first couple layers all the way up to the motion control and environment perception, or even the planning layer, fairly well nowadays, just in the open source world. There are many open source quadrupeds and even a couple bipeds out there that you can do and build at home for, you know, reasonable amount of money, at least in the context of legged robots, which is a couple $1,000s. But they are out there, and so if you're ever interested in kind of studying these platforms, there actually are a lot of open source assemblies that you can look at in Hackaday and a couple other places, as well as open source code. So projects like the Mini Cheetah are very well known for this, where they've provided like all of the controls for just getting a basic quadruped out of the ground, or Quad SDK is another one, as well as all these different hardware platforms from Stanley to Blackbird, Kelso, or the Stanford Doggo. So for the people who are really interested in this, kind of seems really beyond your grasp, you can always go and look for the actual hardware out there, and you can kind of do it yourself if you really wanted to and you're that passionate. You don't need to have a big money pool in order to do it. So kind of going back to what we've been doing, we had a couple of years ago interest in going to full humanoids, which is, you know, we have all of our product suppliers, and so they said, prove to us that you can do humanoids and bipedal locomotion. And so we made this little angry chicken looking robot, which is actually harder to do than most humanoids, to be honest with you, because it's point foot, and that point foot is actually not statically stable, so it always wants to fall down. So it's always taking footsteps in order to stay on its own feet. And so this is actually quite difficult to balance overall, but you can see that we can get a lot of disturbance, rejection capabilities, and self-balancing on the robot. So kind of going from that, we've now scaled to looking at building our own humanoids, and excited to say that in the next year we'll be doing a lot more hardware development and videos. So we already have hardware in the works, and we'll have videos out soon for showing the hardware tests, and based off the simulations that I'll be showing today, with our first kind of prototype product, which is that we'll be showing. You'll notice it's kind of a lot like Digit, just kind of with forward knees instead. But you can actually get a large amount of robustness with this system, and we've shown this for completely just blind locomotion. So you'll see here the robot in the middle. It doesn't know that this step is here, and this is about 0.3 meters or so worth of terrain uncertainty, and the the robot's able to stabilize itself just fine, taking a blind step off of this ledge. It stumbles a bit, but it's overall able to stay stable quite easily, as well as just other unstructured terrain, so like stepping over wood piles that you may see in like a construction site, and if something gets caught in the leg and tries to trip you up, the robot's able to adapt for this and actually stabilize remarkably well. So we've been starting to show a lot of these baseline stable conditions that the robot can be robust and that we can operate it for many hundreds of hours without a fall, even in these very unstructured terrains. So kind of how does this do this? Going back to the planning, locomotion coordination aspect, the high level, you have planning for local steps and path planning or decision making. The locomotion control is then making decisions about where it wants to put its footstep, how much force it really wants to put on that foot in order to actually stabilize itself, and then where its center of mass is going to be going. And you can do this with pretty simplified dynamics. So if you just imagine the whole robot as like a big potato, just a lump of inertia and mass, you can actually get an insane amount of robustness just by using these really simple models at the planning level for the next footstep or two. And then once you have that rough model, you can send it to the lower level where you're doing whole body control, and you're looking at joint torques and trying to generate from that simplified model every single joint torque in the robot. So how exactly it's going to stabilize itself, how much torque is going to go through each system, and what is the order of tasks that you want to do. So maybe I want to prioritize my upper body as a point of being more stiff than my lower body, or maybe I want to have my chest move more in order to complete the task. So you have these implicit priorities and whole body control that you want to kind of tune up and get the robot to perform a task the way that you want it to be. And then it goes down to low-level actuation, where it would actually be executing on the motor control level, and you're doing field-oriented control in order to stabilize a motor. So kind of how these will all flow, at the gamepad kind of interface or a tablet interface for GUI, you'd be sending pick and place commands through a task planner, which then boils back down to your planning level and sends to your control. And then that control is what actually is making your robot stabilize in the real world. So kind of looking at these frameworks, you can do a lot of atomic actions where you're saying, okay, if the robot falls, how is it going to recover? It's going to have like an arm that might brace it, for example. Default home positions or scripted behaviors like picking up boxes or doing all sorts of different prescribed application level tasks, in addition to just like walking around and standing. You can do compliant modes, so sending the whole robot to be passive, so that way you can move it around or you can interact with it how you would want the robot to pose the way you want it to pose. So there's a lot of flexibility in how exactly you want to control this robot and how you want to animate it to do what you really want to do. These are kind of some of the more extreme examples just to demonstrate robustness. So on the left side here, you can actually see the robot walking at, it's hard to tell, but it's 1.5 meters per second. So this is human walking speeds, and we're able to show this very stably for even somewhat unstructured terrains and having a reasonable amount of uncertainty in the ground, or high-speed turning. So if you look at Cassie or Digit or a lot of the other robot platforms, you really can't spin the robot that fast because it'll collide its legs, or it'll just get want to fall over. Because it'll get too dynamic for the robot and it can't control its inertia and angular momentum. But also at the task level. So instead of just like how fast can you walk or how fast can you spin, the task level robustness is picking up objects. So without any control changes, so not much parameter tuning, we're implicitly able to actually pick up objects that are upwards of 20 kilograms to the robot and just not have a whole lot of implicit changes to the inner controller. And having that kind of implicit robustness to what you're picking up or what you might be putting over the shoulders of the robot is a big step in making sure that the robot is reliable across all situations, and that if we do have these really weird tasks, the robot isn't going to want to fall over because we can't observe or we can't be robust to those changes in masses or velocities. So here's kind of just like a really quick pick and place demo showing also some of the uncertainties of the world. So like you'll notice the robot kind of kicked the box a little bit when it was going to pick up the box. And even though that knocked the box off an orientation and position a little bit, just kind of having these compliant behaviors on the underside of things and having robustness in the overall balancing stack, the robot's still able to complete the task. So this will be scaling up a lot more in the next year or two, as you can imagine, when we're looking at warehouse tasks or other applications. And on top of this, it's one of the wonders of doing really dynamic robots like this from a humanoid perspective is that, honestly, it's a very modular control stack. And so we actually use the same control algorithms that we're using on the humanoids that we're using for almost all the other robots that we're building and we're working with inside the house, and future robots as well, or other integrations. So for manufacturers that we might be working with other robot platforms, we can still show an incredible amount of robustness just with the control algorithm technology that we have in-house. So yeah, like I said, kind of a last point with applications to really kind of point out the exact points for getting a generalizable robot and where the money is. We get a lot with unstructured environments and remote operations. So oil rigs are really key locations for this, where you have pipes and all sorts of other things that you can trip over and fall over. But in addition to this, you have a lot of manipulation tasks. So it's not just scanning and reading a gauge, like what you'll see from quadruped companies, but it's also things like pulling levers, opening doors, or doing two-hand tasks like picking up objects and moving them around on the actual oil rig. And those are things you can only do if you are tall, skinny, and happen to have two hands. And so as you kind of go through these requirements, you can start to find a fair amount of places that are suitable for this kind of hardware and autonomy. The other one is constrained tasks. So because we're tall, skinny, and still able to carry large amounts of payload, if you have small spaces like trying to climb inside of a car, or if you are trying to squeeze in between two different conveyor belts and move heavy objects around, you can't get like a big robot do that because you're so space constrained. So you have to have a small robot that's doing whole body maneuvers in order to actually complete that task. And then obviously like bimanual tasks. So having two hands and being able to pick up objects or coordinate and work with other humans are big for things like construction, where you have to pick up a beam and move a beam, or you have to have two hands in order to lay something and tie something down. So these are kind of big R&D areas that we're looking to make big pushes into, and really kind of show that we can be competent in them from an autonomy and robustness level. So yeah, thank you for listening. We're also hiring a fair amount, so if you're interested in working on humanoids, I'd love to talk, and you can apply online, or you can message me. I'd be happy to talk.
Thank you very much.
Yeah, thank you. Yeah, I really interesting to see. As a counterpoint to the previous presentation, that's kind of what it takes, folks, to try and build a general purpose robot. It takes a lot. There's an awful lot that goes into that kind of stuff. One question that I would have, just to get the ball rolling, is your robot has gone for a knees forward approach like humans, whereas obviously a lot of bipeds like Blackbird and the agility robots have the knees backwards, like the emus and ostriches, meant to be a bit more stable. So why have you gone for that knees forward approach?
Yeah, there are pros and cons to each. So with Digit, it's nice because you can have the robot leg space not get in the way of like picking an object up in front of you. With forward knee, you do have that issue, but what forward knee does help with is a fair amount of human environments. So if you think about going down staircases, it's actually quite hard for a robot like Digit if it's going face forward downwards, because its legs will want to collide with the back end of the staircase as it walks down the road, as it walks down. So you can try walking down backwards, but there are other issues that start to really arise with that. And even still, Digit doesn't really have a whole lot of time out with staircases, and there's still kind of, it's an ongoing problem trying to get that robust. Another wonderful thing about Digit's system, though, is that you do have a bit more energy efficiency, but it's not so much so that we really felt the need to convert. And we're finding that we can actually make up be just as efficient with just smarter actuation choices and what we're doing on the motor level. So that's kind of our choice there, while still keeping costs down. So it's a combination of leg morphology and how you're making your motors and how you're going to run your motors.
Interesting. I'd not considered the simple reality of just, knees hitting the back of the staircase.
Yeah.
For all the other fancy things about, perturbance underfoot and how does it handle leaves and gravel or whatnot, just for stairs.
Yeah, you see a crook with Spot's legs. If you look at Spot's legs, you see a little crook in its last joint, and that's partially because of staircases. When it's walking down, you want to have a little bit more clearance, a couple more centimeters to make it a little bit more reliable.
I never thought of that. It's very interesting.
Interesting stuff. One person's asked in the comments, I think they've missed out where you were talking about open source quadrupeds and even bipeds that are available that you can build to replicate. But are any of the tools that you're using open source? To what end is this kind of software approach? Is it an entirely in-house thing? Is there ROS2 involved somewhere, or is that banned from the office being spoken? How does it go?
Right now we haven't released anything open source. We're still debating to what extent we're doing open source, whether or not we're kind of just releasing a black box kind of package that people can use, or have just like public SDK and private internal backend. So we're still debating a couple different things. However, I will say there's plenty of open source repositories for balancing and coordination in legs. So you can look at the MIT Cheetah Code, which is open source on GitHub, and you can also look at ETH Zurich's OCS2 wonderful software library, which is also really great for showing basic robot balancing. So those are off the top of my head 2 really nice libraries to work with.
I can add one to that. I think it's the Toyota Robotics Institute have a physics library for a Drake humanoid platform. That's a very nice API for that kind of stuff.
I've got a question about the serial actuators you were discussing in the beginning, with the kind of spring at the end to allow them to have some level of flexibility when interacting with their environment. What is kind of the performance compromise with those? Do you do you have to sacrifice some accuracy, or are you still able to make these movement models work with those springs to maintain the same level of accuracy?
Yeah, you have to do a bit more controls work in order to keep the same level of accuracy. In addition, because you're going higher gear ratio and you have the spring in the loop now with transient dynamics, you lose a little bit of bandwidth. So that's, like I said, what you like the quasi-direct drive for. So because there's no spring in the loop and it's all virtual, you have a lot of control over exactly how much you really want the system to act like a spring and how compliant you want to be. While the series elastic is just a single spring actuator, and you can crank them up to like 30 hertz, for example, but like with quasi-directs, you can go up to like 100 hertz and still be compliant. So it just depends a little bit on how you want to build your system. The other downsides with series elastic is that they're fairly expensive. You can look at like the cost of a KUKA robot arm, and that should be enough for you to understand why series elastic is expensive.
Yeah.
And there is one day I'll have my PhD work to show, and that's trying to tackle making series elastic actuators on the cheap and hopefully somewhat useful. Really interesting presentation. Again, it's hard almost, there's few questions to ask here because it's so very well crafted frankly. It is a
Yeah,
very good
so
presentation along with the robot itself. Gosh, okay, one final thing then for careers before we move on to our next participant. Careers, is it limited to Austin? Is that
right now? That's our hardware location. We are taking some people for remote work, but that's basically just for software. Hardware, you got to be on site just because there's a lot of you have to be able to assemble things. But we are taking a fair amount of people remote right now. So, but now as we get more hardware in, I think more people will be moving in-house. But like I said, a few people remote right now.
Yeah, well, if anyone wants to get in touch with Nate, he might be the most accessible out of any of our presenters, since he's actually one of the Reddit moderators. So if you ever want to reach out, you just come to our Discord and you can get in touch with him that way pretty easily.
Wonderful. Right, so then the scheduled person at the moment is the no-show, and we knew that, so we can move straight on then to our next presentation, which a returning participant from a fantastic British robotics company, the Shadow Robot Company, who last year came to talk about their dynamic hands, and now are here to talk a bit more about what they've been up to, as I understand, over the last year towards telepresence control and gloves, haptic gloves. So we'll hand over to Ethan Fowler and Rich Walker.
I hope you can hear me okay. First of all, thanks to Reddit Robotics Showcase for inviting us today. It's been really interesting. All the other presentations I've been watching with interest. And I'm particularly looking forward to presenting to some people that we wouldn't normally speak to, because this is more broadly robotics, and even more so getting the questions from those people and having some discussions. So yeah, looking forward to that. I think fire away with your questions in the YouTube chat, and I think we'll collect them and talk at the end and discuss them at the end. So who am I? My name's Ethan Fowler. I'm a team and teleoperation technical lead at Shadow. That just means that my day jobs are running a software team and answering technical questions about teleoperation robot. I've also been a Reddit lurker since 2011, so sort of coming home. Let me switch, get my face out of the way. So, Shadow. I'm not going to read off the slide, but as it says, we've been commercially active since '97, but actually the roots of Shadow go back a lot further than that, to the early '80s. So that's pre-internet. So I was told a story the other day that our founders would print off letters to each other and post them to each other, which I quite like, because it put me in mind of sort of early inventors and scientists sending each other correspondence and letters, although they won't like the age comparisons that draws, but that's what I think of. Since then, Shadow has grown to around 46 employees last time I checked. Our headquarters and R&D is in London. We manufacture our hands in Madrid. We build them all in company. And we have satellite offices and remotees in Bristol, Bogota, Budapest, Liguria, San Sebastian, and Snowdonia in North Wales, which is where I'm talking to you from. We make dexterous hands and robotic systems, which most often involve interactions with humans, which is why I'm talking today. So just a quick list of some of our clients and people we work with. Most of them are obvious as to why we'd be involved with them, but if you're wondering why an airline, ANA, is on that list, they're very interested in telepresence and doing work at distance and interacting at distance. So we work quite extensively with them to try and push the boundaries as to what's possible remotely. Yeah, the others are, you have machine learning, people who obviously want action at distance, like NASA and ESA, and then research bodies and pharmaceutical bodies who want to get people out of dangerous or dirty situations. So this is the product you've probably seen if you know anything about Shadow. It's the Shadow Dextrous Hand. It's our sort of flagship product. It's been sold in some incarnation since Shadow became commercially active. We did make a pneumatic version of it at some point, but at the moment, all of our models that we sell are powered by Maxon motors in the forearm. If you see a Shadow Dextrous Hand in the wild, a good way to tell how recent it is to look for that ridge at the top of the forearm. If it has that, it means that it was produced relatively recently, because that's a recent improvement that we made in response to some issues that one of our customers, OpenAI, were having, where they were running machine learning, and that sort of bundling, uncontrolled motion that happens in early hardware machine learning is very dangerous to robots. And that little ridge houses some mechanisms which we managed to increase the tendon lifetime in these babbling scenarios by in the order of 100 times. So we were very, very pleased with that, and it made the hand much more viable for those machine learning scenarios. You might already know that it's a tendon-driven hand. Each joint is driven by two antagonistic tendons, so one abducting, one adducting. And each pair of tendons goes around, as it comes off the motors, it goes around a cantilevered strain gauge setup. So we measure the tendon forces at the motor constantly as part of our control loop. So that gives us a high degree of force control. The first question we always get asked is, what's the payload? Difficult to define when you're not a simple sort of 1 or 2 DOF gripper. Sorry, I'm going to say DOF a lot. DOF is degrees of freedom if you're unfamiliar. Our hand is 20 degrees of freedom and has 24 joints. That's actually the same as the human hand. So whether you know it or not, the 2 end joints of each of your fingers shares a pair of tendons, and you can't bend them independently. Some people have learned a little muscle trick to do it, but they do share tendons, much like our hand. For payload, if you're in a good power grasp scenario, so you've got your fist wrapped around an object, it can carry about 5 kilos. Movement speed is about 1 second to go from fully open to fully closed. And then one of the other big things that you'll see later is that we do a lot of tactile sensing. So we have different fingertips that we can put on this hand. So we have simple 1 degree of freedom pressure sensors, and then we also integrate SynTouch's BioTac SP sensors, which have 24 pressure values, and they measure other things like temperature and vibrations and things. So we try and be as modular as possible. We find that that's very useful in a robotic scenario, and I'm sure most of our clients agree. And one level at which we do this is with the hand. So sometimes the hand is too heavy, or you simply don't need that level of complication. So we have a whole series of dexterous hands that we make available. Again, I'm not going to read off the slide, but you can sort of see that as you start to try and reduce the weight and complexity, first things you sacrifice is those 2 wrist joints. And then the little finger and the extra metacarpal flex that sort of emulates the human palm flex. And then all you can do from there really is reduce fingers, or you haven't really got a humanoid hand anymore, so you're not coming to us. All our hands are driven over Ethernet, but our driver includes that. So as long as your computer has an Ethernet port, you can connect our hand to it and control it. The control loop runs at 1 kilohertz, and that can be in position or foot. And on the hand, there is an on-device 5 kilohertz control loop that's using those aforementioned strain gauges to get desired tendon forces and also limit tendon forces. So the hand is naturally compliant because of tendon stretch, but also compliant because we have extremely fast control loop limiting forces. So it actually feels and reacts a lot like a human hand. If you shake hands with it, for example, it feels very natural. We offer different fleshes and different thicknesses of fleshes. I think all of those pictures are the hard flesh, but we do have some soft flesh, which is, for example, for our teleoperation product, is much better. Every hand has an inertial measurement unit as well, which is useful when you're waving a hand around on the end of a robot arm. Talking of waving hands around on the end of robot arms, what we've been doing mostly for the past 5 years is our teleoperation system. And the goal here is to move people away from dirty, difficult, and dangerous tasks. So this isn't taking people out of jobs, it's just moving those people somewhere else where they're not going to get hurt, or so they just don't have to travel. The sort of secret sauce here, so rather than just bolting hands on the ends of UR arms, is that we've developed our own inverse kinematics and mapping for both the arm positioning and the fingertip positioning. So we control a 6 DOF arm and a 20 DOF hand per side in real time. So it can mimic the user's palm position and the user's fingertips in real time. We find that latency is crucial for dexterous tasks. On the point of safety, you can probably recognize we're using UR10E arms there. So we inherit all of their collaborative robot, their cobot features. And as I mentioned earlier, the shadow hand is very compliant and in constant control. So we've done things like trimmed people's beards with beard trimmers using the teleop system. We've given massages, not good massages, but safe ones. Last year, for example, a doctor in the US examined my lung lining with a handheld sonograph device when I was sat in an office in London. To my knowledge, that's the first transatlantic lung examination. So at the robot end of the teleoperation system, the human-robot interaction is very similar to interacting with a human because it's a humanoid robot. And since the user is being mimicked by a humanoid robot at the user end of the teleoperation system, it's a very intuitive because essentially you behave like a human and the robot behaves like a human, and anyone interacting with the robot behaves as though the robot is a human. So it's extremely intuitive. We find that we can put people in the system without any training, and we might say to them, there's the emergency stop, but they can pick things up and do relatively dexterous tasks. Of course, there is a learning curve, so our more experienced operators can do more dexterous things, but the fact that you can just pick up the system and use it, we're very pleased with that. Again, we tried to build modularity into all of this, so you can choose between a couple of glove options that I'll talk about next, and that's the big part of the human interface, really. You can have one or two arms and any of the dexterous hands that we previously covered. Even the arms, they're essentially filling the role of a 6-DOF ROS-enabled arm. So any other 6-DOF ROS-enabled robot, we can drop in its place with a very small amount of effort. So I said there were two broad glove options. So there's basically the Shadow glove, which is our in-house glove, or we partner with Haptics to bring their glove to the system. So the main goal of the Shadow glove is to be completely unrestrictive. So any motion you can make with your hand while you're not wearing a glove, you can make while you're wearing the Shadow glove. And that means that you can make any motion with your hand and the robot should be able to copy it because you're not prevented from making that movement. It's lightweight and it's comfortable to wear for long periods, and it's sort of an open frame design, so you can mod it, you can print your own parts for it, you can put your own additions to it. Using magnetic sources on the palm, and there are 6 sensors, one on each fingertip and one on the forearm. Each sensor reports its position relative to the palm in Cartesian and rotation. So we're talking a static accuracy of about 0.38 millimeters and 0.1 degrees RMS, if you want the exact numbers. And you can do that at up to 960 hertz, but we tend to run it at 240 because we find there's no real advantage to taxing your IK algorithms that many more times a second. It has no dexterity impact. In order to locate the palms at room scale so that the robot can copy your arms, we essentially just have a 1/4 inch bolt that sticks out the back of the palm, and we tend to put a Vive tracker on that, but any tracker that you can that will fit on a 1/4 inch bolt, which is most of them, will work fine. So there's no tactile feedback on that glove yet. We're still working out how to do that without restricting the fingertip freedom, so that if you put thimbles on people's finger and thumb tips, you start to get in the way of especially fine dexterous actions where they're having to make small pinch grabs. And we do have ways of compensating for that, but we'd rather not compensate if we don't have to. Yes, but as I said earlier, the open frame design means that you could add your own haptic feedback if you really wanted to. But if you want best-in-class haptic feedback, that's where Haptics' glove comes in. So you may have seen this. It's mainly marketed at sort of enterprise VR. But what we do is we combine it with the BioTac SP Plus sensors on the robot. As mentioned earlier, I think that's 24 degrees of freedom of pressure values, and we map those to what Haptics call tactuators in the finger and thumb tip. So you can feel whether the thing on the fingertip of the robot is flat or has a sharp edge, or how hard it's contacting the finger, for example. We also, the Haptics glove, I don't think you can see them in that GIF, but they have ribbons that run down the back of each finger that can be braked so that it resists your finger closing further inwards. And as I said earlier, we're constantly measuring tendon forces on the Shadow dexterous hand. So we simply map those tendon forces if they pass a certain threshold, and then we do a linear mapping within that threshold. So say, for example, the Shadow hand is grasping something, therefore the tendon forces are high and there's something in the way, then we can make the glove resist your fingers as though there is something in your human grasp, which we find it helps a lot with intuitive grasping and not damaging things by crushing them. So we don't just supply hands, gloves, and teleoperation. We're also involved in more traditional robotics. This GIF shows one of our handed arm systems doing a pre-recorded demonstration where we play Biko, the white good manufacturer's jingle on a virtual keyboard, and then make a Turkish coffee using their new coffee machine. So we often get asked to do things like this when companies want a shiny demo for their conference. If you want to get a bit cleverer with your automation than just a pre-recorded set of movements, we have automation libraries that allow customers to build, pick, manipulate, and place state machines. We also included in that is visual object pose estimation and automatic grasp selection. Obviously, you have many options for grasping, and there's many parameters when you have a grasper this complicated. So we pre-build a library per object and then select one at runtime based on the collision environment around the object and the optimal way to grasp it. Our sort of unique selling point here is that the dexterous hand can grasp a wide variety of objects with different shapes and deformabilities. It's much more flexible than your sort of usual 1 or 2 DOF pick and place robot. And you can see in that GIF, for example, that we're doing some quite useful in-hand manipulation. So we can not only push the plunger on a pipette like that, but there's also a little switch on the front that you use to eject the tip when you're done with it and you want a new sterile tip. And we can even flick that with the fingertip and carry on. And if I haven't mentioned it before, in the top left, you can see move it because we're fully integrated into ROS. It really helps with our modular philosophy when everything acts as a node. And if a customer wants to intercept some data coming from our glove, for example, modify it in some way, and then republish it before it gets to the teleop system, easy. And you can even do it on a separate machine than the machine that we gave you, so you can keep our setup nice and pristine and just make changes in your environment. So I've already talked about teleoperation a bit, but just here are a couple of examples that illustrate some of the things I've talked about. At the top, you can see Joanna, who's our most experienced teleoperator, playing Jenga. Jenga is an excellent test of fine dexterity, as well as being entertaining. We do have to limit how often we can do this test in the office, because if you're a roboticist, you know that we are conditioned over the years to lunge for an e-stop whenever there's a loud noise. So regular crashing of Jenga sets is not good for the general sanity of the office. So we try and keep that to a minimum. It's interesting to note here that Joanna doesn't have touch feedback. So you can see we haven't got those BioTac green fingertips on the robot, and she's using the shadow glove. And yet she's doing a fine dexterous task very well. It's possible that in this case, she has, perfect vision of the scenario because she stood next to the Jenga set. But that might be how she's compensating. But very often we don't have that. So even if you have, say you have a static camera for a remote teleoperation setup, you might need to interact with something behind an object or that's occluded by something else in the scene. And that's where haptic feedback comes in. So at the bottom of the page, you can see Mike from Haptex, and that's not a VR headset he's wearing, that's a blindfold. So he's completely blind. So we've sort of artificially introduced the worst case scenario here. We've completely lost vision. And as he switches his hand across the table, you can see the thumb makes a very light grazing contact with the ball. But just from that, and I should point out, it's a soft ball. It's not a hard surface. He can tell with pretty good, you can see from the confidence he picks the ball up. He knows where it is. And that's the value of tactiles in, for example, the scenario where you have limited vision. So the final area that I wanted to talk about, and this is something of a buzzword, but we are particularly applicable here, I think, because the shadow hand can, optionally I should point out, but it can produce an absolute flood of data. So we have a lot of sensors, tactiles, force, position, velocity, temperature, current, voltage, inertial measurements, and all that stuff is at high data rates. So if you want to do machine learning about hands and grasping and in-hand manipulation, you're kind of the ideal platform. So here's just some examples of things that have gone well so far in machine learning. So in 2019, the Human Brain Project added our simulated dexterous hand to their eBrains infrastructure. So that's the top left image there, and built a tool set to connect these simulations to machine learning frameworks such as TensorFlow. So this enabled training of in-hand manipulation and reorientation of objects. In the same year, Google Brain used the dexterous hand hardware to learn how to manipulate multiple objects. And apparently that GIF in the bottom left was after just a few hours of training in terms of sorting and rejecting objects in the hand. In 2018, this is one of the more famous things so you may have already seen this. OpenAI used our dexterous hand to train in-hand manipulation. It started with cube reorientation, was what you can see in that GIF in the bottom right. The machine has a goal of reaching a particular orientation with the cube. And they initially trained in simulation, and then they finished the training with real hands. That was quite effective. But more impressively, in the top right, you can see that after that, they managed to train their machine to solve a Rubik's Cube in a single hand within 4 minutes, which is something that I couldn't do if you gave me 4 hours. So we were very we were very pleased to see that, because it proves the capability of the hardware, even if you do need a machine learning behemoth to do it. So that was another thing I wanted to mention, was that in order to train that, they trained for only 30 hours, but that was on a cluster of 384 different machines with over 6,000 CPU cores and 8 Volta V100 GPUs. Since then, NVIDIA have released their GPU optimized simulator, Isaac. Sorry, it's not a GPU optimized, but it's also heavily integrated with machine learning. And NVIDIA sort of made a point that they had achieved the same simulated machine learning as OpenAI did in 10 hours on a single A100 GPU. So just the rate at which machine learning is improving is astounding. In the words of 2-minute papers, Carol for her, a time to be alive. The reason I wanted to mention NVIDIA Isaac so much was that you can actually go to their website, sign up for their developer program, and download Isaac now. And because we were part of their press releases and stuff, it's literally, I think it's 2 arguments you need to supply to their standard launch file, I think start.py, and it will spin up 64 shadow dexterous hands in simulation, all learning to turn cubes. So the level of accessibility there is mind-blowing compared to a few years ago. We're also working on some machine learning stuff in-house. Our main goals are improved control and accuracy. But this has been particularly useful to us because now we know what it's like to be a machine learning customer of the shadow hand. So it's led us to make big improvements to the way that we make data available, and we can have much more fruitful discussions with machine learning clients because we understand half of what they're saying now. More broadly on research, we've been supplying academia and industry with our advanced robots for many years, and we've been part of a lot of collaborative projects within the UK and within the European frameworks. So we've had the opportunity to support and take part in a lot of published research. So if you're interested in, the real nitty-gritty of how humanoid manipulation works and how you can emulate that in robots and how you achieve, best-in-class dexterity, just have a search on Google Scholar or something for Shadow Robot, or even just Dexterous Hand or Robot Dexterity, and there's a lot of stuff on there that's incredibly useful. So we're open to ideas and suggestions and collaboration ideas, and of course sales inquiries. So email us or call us to start a conversation if you want to. There's a lot more detail than I could fit in this presentation on our shiny new website that we launched last month, along with better videos of some of the things that I've talked about. So have a look there if you're interested. And other than that, I don't know if there are any questions in the chat.
Go on, Michael, you can start this time.
Yeah, you got it. Well, we're still waiting on some questions in the YouTube chat, but thank you guys so much for coming back. It's been wonderful having you again. Even just seeing the difference a year makes in the kind of progress y'all have made is just really, really fun to see. To start, I guess, to kind of, bring back in Rich's keynote from last year, one of the considerations he was talking about for tactile feeling was the ability to transfer the sensation of temperature. And he brought up a few things that were difficult and a few current research efforts. I was curious if y'all are still interested in doing any kind of temperature sensation transmission, or any kind of what's the current research effort on that?
It's on our list. It's on our list of things that we're interested in, but we've been so focused on just getting the dexterity aspect right over the past year that we've done nothing active in that area. And it's certainly very interesting, and I think if we were going to pursue it actively, human temperature perception is, we think of it as just hot or cold, or on that scale, but it's really, it's also about like flows of energy, thermal energy, and in and out and things like that. So if we were going to attack that, I think that would have to be in a collaborative project with someone who that was their field, thermal perception in humans.
Absolutely, yeah. We do have a question that came up. They may have missed it, but how many actuators do you use to get all the degrees of freedom in the hand?
So there's 24 joints, but only 20 actuators. And the way that the reason for that, as I mentioned earlier, that human fingers are underactuated at the final 2 joints of the fingers. So what we do is we have 20 Maxon motors in the forearm, and then each motor spindle has a pair of tendons which are wrapped sort of antiphase with each other. So they're antagonistic pairs. So motor spins one way, pulls one tendon and releases the other, spins the other way, pulls the other tendon and releases the first one. And those 2 tendons are routed up through the hand, and they reach the joints and pull antagonistically on either side of the joint to produce torque.
Great.
Thank you. Following on from another question here, He asked, would the hand be applicable in prosthetics? I guess another way of putting it is, how far away do you see it from being viable in prosthetics, both in terms of technical requirements and the cost?
There are some huge challenges. I mean, this is actually what brought me to Shadow. I started talking to Shadow because I was interested in these hands for prosthetics, but I got distracted by the shininess and started working for Shadow. But the major challenges are power. So like any robotics, most technologies carrying around a big enough battery to power this thing. It's a problem. Also, that whole forearm is full of Maxon motors, and that's what's required to get even close to human equivalent strength. So if you wanted a prosthesis that could match human grip strength, you've got to, I would say that we're waiting for a step change in motors, but that's not really going to happen because magnets are magnets and they obey the laws of magnets. There isn't really a way to miniaturize these things downwards. This is physics now. So occasionally we entertain some crazy ideas like sort of phase change actuators, like those wax cylinder type things in the fingers, and ways to miniaturize that, but hugely challenging. And then the other thing is the human interface element of it, because most of the prostheses right now, they will sense 1 or 2 degrees of freedom from the user, because they'll use the now vestigial muscle activation as a signal, for example. But to control, and sorry, those 1 or 2 degrees will do sort of a broad open and close of the gripper, or you choose a key grasp, and it will change the key dimension of that grasp with that degree of freedom, with that single degree of freedom signal. So to have a 20 degree of freedom 24 joint robot, the only way that's useful is if you can extract that many signals from the human being. That's not likely to happen, I don't think, at the arm. It might happen at the brain as brain interfaces get a lot better. I think that's a possibility. But yeah, so there's 3 enormous challenges, and that's ignoring the cost challenge as well. It's certainly something that I hope to see in my lifetime. I'll put it on that timescale.
I agree with you on that one. And again, what a time to be alive. Certainly, the right century to see us transition from robots not working to working. A follow-up question: have you tried putting the system on a mobile base?
Yes, is the short answer. So we were chasing that idea for a while last year. There were a few projects that were sort of saying, that's required for this. In the meantime, we've sort of tracked a bit and said, actually, let's focus on what we're good at, which is the dexterity bit. So we've worked with some partners to sort of say, can you just, here's the specs, can you give us a mobile base, and then we'll do the integration. It's surprisingly challenging because you have, especially for the bimanual system, you have 2 UR10s with at least 5 kilos on each one, moving at, humans don't realize how fast we move our hands because we're so good at controlling them. So if you move a UR10 and a 5 kilogram payload at the speed you move human arms, you're asking a mobile base to be incredibly stiff and put up with a lot of reaction forces. And that mobile base also has to, for most cases where people want a mobile base, they also want it to fit through a doorway, fit down a data center corridor. It's a very, very constraining set of requirements. But having said that, watch this space, I would say.
I've got a quick question about the kind of pared down hands that you have now, not just the fully dexterous hand, but the ones exactly those. How have you seen those being used? I think it's a very interesting concept, the idea of, did you make these to make them, so that smaller labs with lower budgets could use them, or maybe, increase the ability of people in industry to use them? Kind of what was the design drive behind this, and how have you been seeing these being used?
I would say the main driver was probably budgets and cost. Yeah, it makes it more accessible. But we do have a lot of conversations with people where they say, we want to use your hand for this task, and we go, no, you don't. It's too complicated for that task. You don't want to program 24 joints just to pick up the same size object every time. So that's where the fewer number of joints and things come in. It's also to do the difficulty in programming a 24 joint robot is not to be understated. It's so reducing the number of joints also just has deployability implications. A payload as well. If someone wants to have a smaller arm, say you're using, a UR5. If you put a full dexterous hand on it, you're left with 700 grams of payload. That's not particularly useful. So if you go down to a hand light, suddenly you have 2.6 grams of kilograms of payload. That's a lot more useful, a lot more deployable. I think those are the main drivers behind it.
Yeah, that's very
the point you make about you don't need that many fingers for a lot of the applications is one that sounds very obvious when you think about it. And I actually think back to Matt Groening, who created The Simpsons, who said the reason that The Simpsons have 3 fingers is because it was easier to animate, fewer fingers, less drawing. So,
we sometimes refer to the hand light as the Simpsons hand. Yeah.
Yeah,
my
first thought.
Can I ask about the glove? So you mentioned the glove is modular. Is the glove itself part of kind of the IP and the Shadow Robot brand and portfolio of what you sell and offer services? That's not something that's open source in a way.
Yeah, that's not open source. There was a lot of R&D development into that, so not quite ready to open source that.
No, fair enough.
But we do have one thing I forgot to mention is if you wanted to just run a dexterous hand simulation, we tend to deploy our software within Docker images. So we have public documentation that just says, pull this Docker image and you can run a gazebo simulation of our hand. And gazebo requires a pretty hefty CPU to achieve, especially with a 24 joint robot, to achieve real-time simulation, but it can be done. So it's actually very accessible. If you just Google Shadow Dexterous Hand documentation, it will come up and you can download it and have a play.
And then you can print your own glove at home.
Yeah, maybe.
And I've seen a few people. A colleague of mine has this year had to design a simplified version for his company.
Yeah, it's unfortunately the most expensive bit is the position tracking system that we buy in and integrate. Because if you want that level of accuracy and real-time control, then there aren't many things on the market, especially that aren't optical and therefore very victim to hand occlusions when you make fists and things like that.
Okay, wonderful. Right, Michael, do you have any more questions? Oh, here we are. Wonderful. Our next presenter has arrived. So if there's any more questions to ask, Michael?
I think that's pretty much it. Thank you guys again for coming and presenting. It's been wonderful having you.
Thanks very much for having us. Thanks.
Yeah, thank you. Yeah, really great to see the update and to see the progress. And thank you again for sharing with the community what you're working on. It's really great to see an example of a premier robotics company certainly doing this kind of work.
Thanks very much. Yeah, been really interesting.
Wonderful, thank you. And so with that, then we will go over to our next presentation, a 6-axis dynamixel robot arm by Mel, if I'm pronouncing that correctly. If not, please correct me.
Oh, you're muted.
You're muted. You need to unmute your mic.
Mel, you're muted. Yeah.
Okay, sorry. Do you hear me?
Yep, there we are. Wonderful.
Okay, perfect. So thank you very much for having me in this event. And yeah, this was quite interesting so far. So my name is Maël Abril, and I'm from France, near Bordeaux. Currently, I am an apprentice in industrial automation, working in a small company, making mostly PLC programming. And next year, I am going to mechatronics engineering school, still as an apprentice in the same company. And so a few years ago, I started making some robots as a hobby. And I'm going to tell you today about the robots I made, and the one in particular, which is the one I am the most proud of. So let me just screen share. Okay, so very briefly, I am going to go over the different robots that I have made over the years. This is the first one I ever made. As you can see, it is quite simple, made from Lego and pieces of wood. And it is a RC robot that uses RC plane hardware. A few months after that, I I got a 3D printer. So I decided to make another version. So, wait a minute. Okay. So I made the second version of the same robot using a 3D printer. And there is a little video of it just picking up a stick, going over some obstacles, and putting it back in another glass. And around that time, in class, I had classes of industrial robotics on some Fanuc robots. So there is a video of this class, and I became really fascinated by industrial robots. I found that the motion is very beautiful, and from a technical point of view, I just think that they are very, very, very interesting. So I decided I would try to make my own 6-axis robot arm. This is the first version. It is made using dynamic cell servo motors, and every joint is just directly attached to the servo. And even though it was quite cool and it was very fun to make, it still had a lot of design issues. Like, for example, the wiring is very messy. I didn't really plan for the wiring in advance, which is kind of a bad idea. This is my latest robot. It is a SCARA robot that is still a work in progress. I am working on the software to make it draw any image. And this is the robot we are mostly going to talk about today. So this is a 6-axis robot arm that is the second version I made. And it also uses dynamic cell servo motors, but this time the 6 joints are actuated by the same small motors, and the first 3 joints have an additional reduction with a gear and with belts and pulley, because the first 3 joints need more torque and less speed than the joints from the wrist. So what goes into making this kind of robot? So the first thing is choosing the hardware, most importantly the motors and the control system. So the dynamic cell servo motors have a lot of advantages compared to classical hobby servo motors. The main one are that they can give position feedback as well as current feedback, and a lot of other advanced control features. You can, for example, tune their PID parameters, and that allows to go much further in terms of application. So the first step, the second step after choosing the hardware, is to make the 3D model, the mechanical design. I made it on Fusion 360, and here is a little video of it, of model that shows the complexity that goes behind it, and there is maybe 50 screws still missing from the model. So making the 3D model is not difficult, but it is a very long task. It takes a lot of time, and you have to be focused, but it is absolutely essential. First, because the robot is going to be 3D printed, so of course you have to have a 3D model in order to be able to 3D print it, and also because it allows you to see design issues before you make the parts. So a lot of parts have been designed and changed a lot of times because the 3D models allowed me to see problems, to see, for example, collisions between pieces that I wouldn't have been able to see otherwise. Then it was time for the electrical design. Thanks to the dynamic cell servo motors, the design is quite simple. So here is the whole design. So the dynamic cells are able to be connected in a bus, which means that there is only 3 wires that goes to all the motors, and then they are communicating using some protocol made by the manufacturer. And as you can see, there is only 4 main components: the Raspberry Pi, on which the software is running, the communication converter from the same company that makes the motors, a power supply that is 5 volts, since all of the hardware runs on 5 volts, and the 6 motors. So the electrical design is quite simple, which is a big advantage of dynamic cells. So here is the final result. I'm just gonna leave it. And by far the most challenging part of making this robot was the software. I programmed the software in Python almost from scratch, because I just wanted to see if I would be able to make it, and it turned out I was. So the challenges are first the inverse kinematics. So inverse kinematics is the answer to the question: given a desired position of the tool in space, what should be the position of each motors to achieve that position in space? And for a robot like the Scara robot, for example, it's quite simple. With a bit of trigonometry, you can just get a simple formula, a one-line formula that gives you the results for each joints. But with a six-axis robot arm, it's more complicated. You have to use metrics, and the computation takes a lot of steps. And the other main challenge was making straight lines. So since the robot is made of six rotary joints, combining those 6 rotations into a linear motion is quite hard. And the main limiting factor was the communication delay with the motors. And at the end, I achieved the linear motion by plotting 10 points per second on the line that I want to follow, and then the robot is just going to follow those points on the line. But you have to work a lot on the timing to get it to look good, and then you can just make it do straight lines and turn around the TCP. And turning around the TCP cleanly was my goal with this robot. But when I saw that it worked like that, I was just so happy I couldn't really stop smiling. And so to finish, I'm then just going to show 2 little videos. So the first one was taken at my workplace. It is the meeting between my little robot and a real industrial robot, which is a Yaskawa GP7. And it was a really fun video to make. So the 2 robots are just wired to a push button with 2 contacts, one wired to each robot. And every push on the button triggers the next move for the 2 robots. So it's kind of a cheap trick, but it works good enough. And the last video that I'm going to show was taken in class during my technician degree. We had a class project which was making a small scale model of a pallet stacking machine. So we had some very little pallets that were printed, and they were just the right size to be carried by my robot. So I thought it would be very fun for the presentation of our project to get the robot to take pallets at the exit of the machine. And so the next video is one of my mates made for TikTok, and you can see the robot being the robot stacking some pallets. So actually, the robot detects the pallets automatically from the current in the motors. So it just waits in position. I put it manually in some position. Then it just waits there, and when it detects a current increase, it will stack the pallet on the next one. So this was quite fun to make, and it worked really well during the final presentation. Unfortunately, I don't have a quick video of the presentation. So yeah, this is my robot. I am quite proud of it, and I'm definitely going to keep making robots and make them better and better as they already have been better and better since I started.
Yeah, thank you very much, and you absolutely should be proud. That is a fantastic robot. We often get, people ask on the Reddit robotics subreddit, they ask, I'm new to robotics, can I get involved? And often people ask, I'm in this career, can I transfer and can I get involved? And I think I'm probably going to share this particular presentation as a great example.
Absolutely, yeah.
The way that you the way that you started with a very simple robot that is just, there's nothing wrong with a robot that's made of cardboard and pieces you found around the house.
Yes,
it works.
Just
and
fun.
You can see how you've progressed to learning 3D printing, learning CAD design, and then getting into motor control and transmission, and then finally through to the kinematics and the computer science. And you can see the step-by-step progression through each robot, and it's really fantastic to see that journey.
Thank you.
It looks easy when it's done in a 10-minute presentation, doesn't it?
Yeah, but it was a few hundred hours of work. So yeah.
No, I can fully appreciate that. So someone is asking, is the ARM on GitHub? Is that something where people could see? Wonderful.
Yes, absolutely. So it's my pseudo of GitHub is the same on Reddit. Liamarl, Liamarl, and you can check it out on my GitHub.
I've just copied the link into the subreddit. We will be uploading the information that everyone submitted to the website after this showcase. We ran out of time to do it, truthfully. So I personally have had a lot of beef with the dynamics of motors. I know quite a lot of people who find them to be quite painful to work with. Did you not find that? Did you find they were just easy out of the box to use?
For me personally, yes, because I use them with the Python library, the Dynamic Cell SDK Python library, and there were quite a few examples of code, and I just copy and pasted the example codes and kind of modified it to get it to work. And yes, for me personally, it was quite easy to use. That being said, it depends on which models, because for example, on the first 6-axis, I use the AX12A from Dynamic Cell, and that one I wasn't really pleased with it because it didn't have PID control and it was much less precise. And for the price, I didn't really like it. But the small ones that I use for the second version, honestly, they're very well. I'm just really pleased with how they worked.
Yeah, that's interesting. For the inverse kinematics for your robots, did you use like an off-the-shelf solver that already existed, or did you write your own from scratch?
No, I wrote my own from scratch. I just use NumPy for the matrix computation, but I did it myself.
Very nice. All right.
Very impressive.
So that makes sense. I have a background in mathematics, so it was kind of easier since I already understood very well matrix and rotation matrix and stuff like that.
Absolutely. Yeah, it makes a lot of sense.
So what kind of projects do you have in mind next then? And what kind of skills are you planning to take? Well, what is your motivation for your next project? Is it to try and learn a skill or to build a certain type of robot, or thinking ahead to what you'll be studying in the future?
Okay, so my next project will be very, very small. It's kind of funny. It is to make a robot to play a kitten that friends of mine got. So just a robot with 2 axes and a little wire to make the kitten play. But for my next very serious robot, I already kind of started working on it, even though it is preliminary design. But it will be using stepper motors, and I want to make a 7-axis robotic arm. And I would like to kind of use a robot operating system or other software that I know that I was able to make all of the software by myself, but it's still very limiting, and I just want to use something off the shelf that will allow me to go much further into what I can do with the robot.
Yeah, certainly. At some point, if you want to go, especially if you want to push towards the research aspect of robots, or making them with a fancy sensors, then learning, or making an effort to learn ROS2 will be the way to go. Because then, of course,
exactly.
You don't have to write all the code. You can just take someone else's and install a package and run it. And
yes, that is the plan.
Yeah,
that's the plan.
But it's great to have the foundations that you have first, because it means you're not reliant on it.
Yes,
you'll often find the ROS package, is actually very slow, and you can take the important bit and cut it out and just use that.
Okay.
Or things like that. It's just, you've got the core skills before you go on to learn ROS. So well done for that.
Yes, exactly. And I truly understand how it works. And by the way, kind of off topic, but tomorrow morning I'm going to program my first real industrial robot in a factory. So I will also be able to apply a bit of the knowledge that I got from making robots. So that would be very, very interesting.
Interesting, and it's fun to you'll be able to compare building it yourself versus working with an industry built one as well.
Oh yes, it's really not the same thing at all.
Yeah, it's a big old difference.
Yes, absolutely.
Okay. Well, Michael, unless you've got any more questions yourself, then I think we'll move on to our final, but certainly not our least, in terms of presentations.
Sounds great. Mail, thank you again for presenting. This is great to have you.
You're welcome, and thank you to you for organizing this event.
No problem. It's good fun. We enjoy it too. Wonderful. So we've talked a lot about human-robot interaction over the last couple of hours, in terms of how we can, design robots to interact with us. But then here we're going to see a bit of the opposite side for how humans can interact with robots in terms of art and emotion. To explain more about it, here is Laura Smith, no relation.
Yeah, that's right. Right, I'm gonna get my screen up. Hopefully this goes smoothly. Right, so hello everyone. My name's Laura, and I'm a recent graduate from Oxford Brookes University with first-class honours in fine art. First and foremost, just want to say what a great opportunity this is to reach out to people interested in robotics, maybe even art, and I hope today I can just show you rather different sides. Now, I'm going to put it out here now, I am by no means a scientist or an engineer, as you'll see, but I approach art making from a surreal perspective, you could say. I'm also a major advocate for collaboration. I found that working with participants from varying fields brings unique research, sensibilities, and textures to my own works. So today I'm going to be giving you an overview of my practice. And so the first half of my presentation covers my research. The second half goes more into the build process and mechanics of my robotic tentacle. Ultimately, my main aim of the talk is to kind of illustrate the possibilities of combining art and robotics and how it can be really engaging for the viewer. So as an artist, I am disquieted by the conflicted relationship between humans, animals, and technology. I would normally describe myself as a traditional sculptor. However, over time, I've been experimenting with merging sculptural processes with digital media as well as robotics. And when the pandemic kicked in, I had to completely rethink my approach to art making. So without studio access and lack of technical support, I had to outsource expertise from overseas. Engagement with technology, particularly robotics, suddenly became a way for me to think beyond the human and open new ways of thinking about animals and these ambivalent relations. So my piece, Cradle to Grave, was the first time I utilized robotics in my practice. I constructed a motion following robotic crow from my household waste, and it was a piece critiquing hypercapitalist society, especially with respect to ecological issues. But generally speaking, I find it incredibly ironic how my works concern the natural yet always pervade into the machinic. I deploy robotics purely as an aesthetic engagement device. In fact, it's intended as a form of critique, highlighting the desire of humans to assert their control or manipulate the non-human world for their gains. And yes, that's a rather dark statement, but my practice is all about kind of promoting conversations more than anything. In fact, one of my favorite robotic artists, Marie Deprise, in her installation Autonomous Times, imagines a future where humans might need to tame or domesticate their artificial creations. And like Deprise, I utilize the robotic form to kind of extrapolate and speculate the slippages between technology and human interaction or intervention, whereby power kind of shifts constantly. And I find that the aesthetics of movement, particularly nervous or compulsive activity, are essential to the viewer's experience and was something at the forefront of my mind when creating my installation. And on a more personal level, engagement with robotics prompts many questions for me, like what, for example, would a machine with the essence of a non-human look like and be like? And what would this say about the current state of the world? Like all my works, my project began with fascination, weaving in of many different philosophical thinkers. Thematically, not really about one thing. I believe the meaning is subjective and shifting, but as a paradigm of thought, the octopus seems to defy boundaries. I'm interested in this transition from a human-centered worldview to biocentrism, so the human as part of an ecosystem. So systems, interconnections, networks are essential to my practice. And in The Mushroom at the End of the World, Anna Singh suggests precarity, so the condition of being vulnerable to others and how unpredictable encounters can transform us. Thus, the inability of control, not even of self, has also become a characteristic of my artistic process, so a shapeshifter in a metaphoric and a procedural sense. So I guess at the crux of this installation is how do we expand our worldview beyond ourselves? Now, if I was to categorize myself, I would say that my work is heavily research-based. I'm particularly intrigued by dialogues surrounding the Anthropocene, so a geological epoch that reflects humanity's impact on our planet. And in human to animal studies, the Anthropocene is analyzed with anthropocentrism, so a theory that prioritizes human beings above all else. So at the heart of my research is this deep concern that we are increasingly disconnected from other life forms. And if we're looking into the future, can humans be wholly trusted to make wise decisions as technology advances? And can this reflect our world's prismatic diversity? And of course, I'm going to go into a bit more detail about these lines of inquiry and some of my key influences. So from a theoretical side of things, my installation responds to the writings of American theorist and scholar Donna Haraway. And in her book, Staying with the Trouble, she promotes a kind of urgency not to think in categories or binaries. Tactile thinking is an epistemology that explores new ways of thinking like an octopus, using this being as a metaphor for a nonlinear networked existence. So in essence, we're not sole harbingers, we are made up of billions of bacteria inhabiting our guts, and like an assemblage of many different life forms. And like Haraway, I'm interested in these ambivalences, contradictions, multi-species models, shapeshifters, tentacles, guts, tangible beings. My work does not really attempt to provide answers, it prompts playful reflections. If anything, it's a very unstable experience inhabited by a lot of problems. So with tentacular thinking in mind, I went a bit fast, I began kind of researching the octopus. And in recent times, their adaptability, control mechanisms, their intelligence have captured the attention of bioroboticists and scientists, engineers. So they're kind of like a boundary subject connecting varying fields. And in his book, Other Minds, cephalopod expert Peter Godfrey-Smith challenges what it means to think and feel. He describes the octopus as like the closest thing to an intelligent alien. Their skin is like an antenna, skin screen, seeing skin. So what would it be like to have a protein body or a body that's all possibility? I mean, even their nervous system is unlike our own. They lie outside the usual body-brain divide. Their arms are partly self. However, one of the most unnerving discoveries I made was that Spanish aquaculture company, Nueva Pescanova, is fast-tracking the opening of the world's first octopus farm to 2023. And there are also claims that attempts are being made to genetically modify the octopus to accelerate industrial aquaculture. So essentially, they're trying to turn the octopus passive to prevent them from turning on one another in captivity. And leading on from this, the other strand of my research concerns the ramifications of emerging genetic technologies and how they've altered the way we choose to represent and understand life. I've been looking into things such as the trend of biohacking, so a person who uses science and technology to make his or her body function better or more efficiently. So technologies like CRISPR now allow humans to modify the cells in their bodies. So at this point, science fiction is practically the new fiction. And as an artist, I feel that my main intention above all else is to prompt engagement and discussion through an immersive experience. I'm very disturbed by this idea of nature as a raw material manipulated by the biologists, like constantly trying to categorize and map. The Human Genome Project utilizes DNA as something that can now be programmed, cut, pasted. Organic beings are deconstructed, hacked, and rebuilt. And I find it problematic to reduce things to their simplest forms when life is so much more complex. And although my work is not intended as an ethical provocation, these unnerving dialogues between humans, non-humans, and technology are inevitably underlying. Like with Nueva Pescanova, this attempt to modify the octopus into a kind of passive, autonomous subject is not really surprising, given how non-humans remain primarily excluded from our intelligence, justice, rights. But it's all fraught with cultural complexities. And during a time that, in my opinion, could be categorized as an age of disembodiment, materiality in my work serves as a way of reconnecting to the present. So as a sculptor, I'm naturally drawn to visceral materials, which serve as kind of motifs through aesthetic juxtaposition. So, for example, non-living, living, mechanical versus natural. And I do this as a way to communicate this fragmentation between humans and non-humans. But my interest in the unfamiliar and its bonds with organic matter inevitably led me to SCOBY, which the symbiotic culture of bacteria and yeast, and they produce these flexible cellulose films, which you can see in the images. And the mother scobies, they have almost roles, like the resonance of like human flesh, and well, microorganisms, after all, essential elements of our bodies and identity. And I would say they appear kind of octopus-like. They're kind of strange, adorable, kind of robust, ephemeral, yet enduring. But there's still so much yet unknown about SCOBY. But I feel it offers many opportunities, many applications, and I understand that it's being investigated as a sustainable alternative to textiles. However, for me, kind of embracing process and experimentation has become a significant testing ground to imagine these other forms of life that we can barely comprehend, like that of the octopus or SCOBY, and perhaps as a way to break fixed boundaries and think about, viewless thinking. So this kind of leads me nicely onto what I call speculative hybrid forms. And my conceptualization, this is an assemblage of disparate fragments. So in the case of my installation, it's the contrast between the organic SCOBY and the mechanical robotics, which then instigates this kind of uncanny experience or encounter. And when I visualize a hybrid form, I'm drawn to Haraway's notion of the cyborg, so a creature simultaneously animal, machine, natural, and crafted. So after kind of digesting all the research and feeling kind of overwhelmed by it all, I eventually concluded that I wanted to create something interactive. And although the piece tackles arguably dark themes, I like to leave my artworks very open-ended. I feel that it's important to let the viewer make up their own minds as to what I'm trying to say with the piece. Again, meaning subjective and shifting. So I began brainstorming how I wanted the robot to react or respond to the viewer, and I also knew that I wanted to utilize my scaly skin as a sculptural material. So overall, I wanted the aesthetic of the robot to have this kind of Cronenberg sci-fi-esque feel to it. So the initial criteria I came up with is that I wanted the arm to kind of sense the presence of the viewer and respond or modify its behavior, and create the illusion of sentience, like this idea of it being able to coil, wrap, or mimic movement in some way, and react to certain stimuli, such as it may become afraid if someone moved too quickly. And the other thing I was considering was a color changing element, because octopus's moods correspond to different colors. So that could have been interesting. But I achieved none of it. And if I'm being truly honest, I did not expect to face as many challenges as I did, but we're going to get into that. So you may be thinking, how on earth does an undergrad with no knowledge of robotics or code, for that matter, do something like this? And as you can imagine, it's pretty tricky. Rendering such abstract ideas into something perceptible requires a mediation of technical probes, sensors, and most importantly, outside knowledge, especially since I was unable to get support from uni due to COVID. So this is where my good friend Calvin came into the picture. So I came across Calvin a good year ago now on a site called Instructables, where he helped me with the motion following element of my robotic crow. And our relationship's pretty much blossomed from there, really. And naturally, once I knew that I was going to need to find someone who could code, I was just gonna lure him in. So early on, I voiced to Calvin that I was basically trying to delve into the realms of human-machine interaction, which I understand is an active area of research and is not trivial. Calvin and I had lots of great ideas regarding how we could simulate the type of behavior that I was after. But the most exciting idea by far was what Calvin called a mood matrix. So utilizing environmental sensors to affect the robot's mood depending on the sensor inputs. So if it was warm and there were a few people sensed, it may make the robot anxious, but we could also take the same idea but use sound levels instead of temperature. But sadly, did not get to implement any of these elements into the project. And in an ideal world, I could have really done with hundreds of thousands of pounds for the parts alone, as well as a lot more research and development time. But hey, I had about 3 months to try and bring my crazy vision to life one way or another. So here we go, DIY mechanics. I started off with a very basic setup. The early prototype was essentially a puppet with 2 wires to manipulate the movement. For the core, I used a speedometer cable, acrylic vertebrae, and cord grips for the spaces. Now, as you can see in the video, the movement was all right when puppeteering, but there was also a strange actuation that was happening. And so I experimented with sponge and less space between the vertebrae, and sponge had great give and flexibility, but after a while it would become congested, which would then prevent the movement even more. So in the long term, it was just never going to work. And aesthetically, just kind of wasn't doing it for me. The second thing I had to consider was where I was going to place the robotic parts. So came up with this idea of using the morphology of the octopus as inspiration for the structure, which was essentially a large piece of sterling board from the garden. And it was just great for fixing into and making like inevitable alterations when necessary. But it was at this point, however, that I knew that I needed to do some more research, and I was particularly struggling trying to translate puppeteering movements to the servos, and felt that rethinking the design may be the best solution. So this is when I came across Asmat, as he's aptly named, the creator of Cyborg. So I thought that was pretty perfect for what I needed. And he sent me these 2 papers that he'd written. And from what I understood from these papers, with continuum robots, you need to drive all the motors, especially opposite motors, simultaneously to reach the desired motion and prevent cable slack. And it basically explained why I wasn't really getting very far. Calvin and I then went on to have a Zoom meeting with him and to learn more about his creation, TacoBot 2. So this is his robot in action, which was like initially designed for agriculture and tomato harvesting. So it has this sliding disc and backbone mechanism that ultimately allows it to move in this helical motion. And he outlined that like a lot of the common problems with arms like this is things such as derailing, like tension, cable slack, low rigidity, low accuracy. So kind of a lot of things that I had to tackle myself over the duration of the project. And from this point, I completely like revamped my arm, switching out the speedometer for universal joints, as well as adding in compression springs. Now, if I had a ton of money to throw at this project, as well as top-end equipment, then I probably would have taken Azmat's approach, and I have no doubt that everything would have worked fine with no uncertainty in the motion of the tentacle. But of course, this was very unrealistic for me to try and achieve on a student budget. So Takabot 2 was kind of what I was going for, but not really what I got. And as time was starting to tick by, I knew that I would have to potentially reevaluate my own ambitions and expectations for the project. I mean, that being said, my new design comprised of universal joints, Azmat's vertebrae design that he kindly allowed me to 3D print, 4 servos with 8 wires in total, 4 of which were tied off halfway down the arm and the other 3 tied off at the end. So my next task was to figure out what I could use as a core for the universal joints. And this changed a lot over the course of the project. So I started with plastic rods, then nails, until I eventually discovered that a threaded bar with nuts to kind of fix them in place was the best way to ensure that the universal joints would stay central between the vertebrae. Because as you can imagine, if the universal joints were not central, this would not help the movement. But frustratingly, I didn't make that change until weeks before the show. But again, hindsight, beautiful thing. But if I had learned anything from the early prototype, the core was necessary because pulling wires without one did practically nothing. And from talking to Azmat, I knew that in order to create a kind of S shape I was after, I needed to create a kind of seesaw motion where the 2 synergistic pairs work together. Now, this was probably one of the best movements that I got from the arm. However, it was like only making that shape for all the wrong reasons. And shortly after I took these videos, the wires just snapped because they were continuously wrapping around the head of the servo motor. So to counteract this, Calvin suggested that we would need some kind of wheel to act like a pulley. But looking back from a convenience and performance perspective, I wish I just bought Dynamixels so that I would have been able to drive the servo motor exactly how I wanted. So these were Calvin's initial CAD wheels to attach to my 4 continuous servos. But I was very disappointed with the print quality, and the groove around the edge of the wheel was practically non-existent. So I decided to make my own. So I ended up using cedar, mainly because it's super light and perfect for the servo horns to be like screwed into. I then drilled a hole into the center of the wheels, which I could run the wire through and then round into the groove. So the 4 wires in the middle section had to remain in tension state and were attached to the top part of the chain that dangled just above the center of the main structure. And the other 4 were connected to the bottom and ran up through the center over a Pringle container, which I put a metal ring around to stop the wire from cutting through, and then connected up to the servos. However, when I switched it on, it would work fine until the tension would begin to release and slack off, causing a loop to form, which would then wrap around the neck of the servo instead of going into the groove, and once again causing the wire to snap. And it was also at this point I switched from fishing wire to steel wire, again, something I wish I had done way sooner. Calvin coded my laptop so that I could control and calibrate each individual servo, but mainly so I could stop them from continuously spinning and inevitably snapping the wire again. The other things we implemented to stop the servo wrapping issue was to use a bracket to guide the wire to the right spot. However, when all were on at the same time, that's when we ran into problems with overtension. This is where the implementation of a pre-tension mechanism became necessary. So I needed to find something elasticated or springy that allowed the wire to bounce up and down with the movement and help with unnecessary slack. And so initially I started with having the wire run over just rubber bands. And although this worked, the steel wire began wearing them down. But at the end of the day, I had to just use what was available to me at the time. And I ended up sacrificing some bra straps and hot glued small tubes that kind of sit in the middle of the straps, which the wire would run through to stop it from cutting into the fabric. Surprisingly seemed to work pretty well and did compensate for some slack. So this is one of the videos illustrating the tension issue I was having. It was at this point that Calvin suggested fixing the rods into the middle of each vertebrae, so to help prevent kinks. So I immediately switched out the nails for threaded bars. I experimented with only partially winding up the servos, because of course having them all wound up wasn't going to help. If one side was tight, the other needed to be released. So essentially I needed to aim for a constant tension, not loads of tension. And I certainly found trying to figure that out like extremely challenging. But the last real technical problem we had to navigate was ensuring that the robot wouldn't be running constantly. The degree show was a week long, so it was important that it didn't burn itself out. So we decided that the cheapest and easiest way to do this was to use a camera. And a friend of mine kindly let me borrow their Raspberry Pi 3 as well as an SD card to use my camera that I stole from my Crow. So literally in the last 30 minutes before the exhibition opening, Calvin managed to code the arm so the movement would only start if a person was detected and of course stop when no one was present. So getting that sorted was a massive relief for me. But it was so funny because like the amount of people who walked in not really expecting it to do anything and then for it to suddenly be triggered by their presence was just hilarious. But overall, a lot of blood, sweat, tears went into the project, and frustratingly, the day before the private view, there was a mechanical issue, which I wasn't able to fix in time. So I was just relieved to see it do something in the end. Calvin and I went into this with limited knowledge, I'd say, in the fields. And of course, like I said before, like hindsight is a beautiful thing. It was pretty gutting to have to compromise my vision, primarily as a result of my budget. And although it was nowhere near what I had envisioned, it was still lovely to and rewarding to watch people interact with it. And it was very effective at kind of capturing viewers' attention and engaging them enough to want to learn more about the project. I also feel that as a sculpture form, it was certainly very unnerving. Like merging the organic matter with the robotics certainly gave it this kind of uncanny edge. But in the future and with funding, I would love to revisit the project and perhaps attempt this idea of a mood matrix, but most importantly, just getting it to move and respond more effectively in general would be the desired goal. But yeah, thank you very much for sticking with me during this presentation. Quite a long one to end the day on.
Thank you for presenting. This was fantastic.
Thank you.
Yeah, absolutely delightful, and all the comments are very positive too. And I mean, we've all got our own questions in this from the audience, but I'm guessing you didn't see the earlier session from earlier on today.
No.
So the keynote speaker has popped back on to introduce himself, Dr. Matteo Russo. He works with this kind of snake robot arms that you described on the very high end. So I'll hand over to him.
Please do.
Well, hello. Hi. I have a lot of questions actually. I'll try to keep the shortest one for now, and maybe I'll ask the others later. I was curious about what you're looking for when you speak of motion. So what are you trying to reproduce with the snake robot in your art? Are you trying to get some kind of like natural looking motion, oscillatory motion? Would you be interested in something that looks smooth and natural, or like more alien?
I think initially I wanted something kind of natural, but I kind of knew very early that was going to be really difficult to achieve. Mainly I just wanted to be more reactive. So we had it on kind of like a timer, so it would kind of do a bit of movement and then stop. So I kind of wanted it to kind of be more organic in its movement, just so it would create more of that sentient illusion, if that makes sense. But I think now I'd probably be aiming for something probably more alien and not really striving for, you know, something like natural in a way.
And so are you planning of like, well, you said that you would like to revisit these. What would you change if you could revisit these with more funding, more budget, or like just like a more complex design?
Oh, honestly, so many things. I mean, firstly, I had like just the overall printing quality. Like even the last vertebrae that you can see here, like they were not well printed. And I mean, I was using the 3D printer at Oxford Brookes, and you'd think that it would be great, but in reality, I was literally having to like drill in the holes where there should have been holes, and like, but yes, that would have been great. But also just like I said, dynamic. I would have loved to have used dynamic saws or something. Like I don't know, but I was just really, I just wish I could have made it less DIY, although I guess that kind of gives it a bit more charm in a way. But you know,
well, I'll say on our end, we're all seeing this as very much a much more professional effort than I think any of us had as an expectation going in.
That's stubborn. I hated
The
compromise.
fact that you're thinking ahead to how this would be done with dynamics alarms, and the fact there's you talk about the elastic compliance that goes into that. It's very advanced robotics. I've spent the last few years studying.
It really is, and I have no knowledge.
Well,
I'm absolutely a struggle.
Go ahead, Matteo.
Yeah, if I can add something
Sorry,
there,
what was that?
like most of the challenges that you had, like how do we get it to move perfectly as I want and stuff like that. My lab has been designing these things for like, I think 12 years now, and we still haven't solved those problems.
Yeah, exactly.
So,
and as Matt said, the exact same thing. And I was there like, surely, like, come on. But, you know, I know now.
Yeah, if you have time to go back and look at the earlier presentation from today, not to be too on the nose, but Matteo's snake arm is like the Rolls Royce.
Oh, I bet.
It's really incredible to look at. So I would definitely, like, if you're talking about, you know, what kind of thing could you build with just crazy high budget, crazy high manufacturing, you know, complexity, this is the one to look at. It's really incredible. Yeah,
I'm just glad I didn't follow it. Straight up.
Well, no, it would have been good to contrast and to see how it would have done well to stand up alongside it. And we've had lots of kind of different projects from the very amateur quadrupeds through to startups, and the same with all kinds of different things. There's a couple of other questions, I think. Did you kind of showed a bit of the inspiration of other robots, tentacle robots you've drawn from, and you mentioned particular Azamats. Was there, and the biological aspects of it too. Any other robot arms come into play? Any other existing work or existing art that factored into it?
I mean, I sorry, it kind of cut out halfway through there, so I didn't kind of hear everything that you said. But this piece, I didn't really speak about it. What was it? The autoprocessor and this kind of arm I was looking at as well, which I'm sure Matteo's seen.
We all know this, though. Yep.
Yeah. God, I'm trying to think off the top of my head. No, because to be honest, I was kind of drawing off, various robotic art pieces, not necessarily that kind of looked like a tentacle, just kind of more interested in like the robotic parts, how they were kind of achieving like a sentience almost. Like it was more that than, I think, you're kind of strive to be a bit original, and you don't really want to be copying too much, a little bit.
Yeah, well, very cool. Anyone else have any more questions?
Again, I'll just feedback another one of the comments. A nice, very different to the others I've seen this weekend, and great to put the art in Steam. Yep, I'll go for that one too. And often when I've done one kind of art engineering project, and I can say it is really good fun, and it's very both therapeutic and also very challenging to have to work with people on.
It's so interesting.
Opposite sides of the
100%. And obviously, me and Calvin were doing it through Zoom, like, and like during like getting ready for the private view, and I was like, oh my god, like I've got 30 minutes and I still haven't got anything. So yeah, it was crazy stressful, but again, like it's great, and me and Calvin hopefully work together again. So, or anyone else who's interested.
No, and I would also recommend to anyone else there in the community who's watching to say, often when you look at the robotic art that's out there, you think, oh, I could do that. And part of that is that yes, you can technically, and also go on then, give it a go.
Yeah. There's a lot more that goes into art than people think.
Oh yeah. I the one bit of kind of robot art that I did, I had to explain them how sine curves work and how a cam can make that motion happen. At the same time, I once uttered the phrase "fabric is fabric, isn't it?" That didn't go down well.
Oh no,
that's rough. No, I was going to say, from your earlier discussion of using things like foam, as the spacing material to kind of this work, I kind of like the idea of exploring the material use for this from a standpoint of, making it look and behave a certain way rather than, okay, what's the best material for performance?
Definitely. And to be honest, all the materials I used were not high performance. I was using SCOBY as well, which is, no one really knows much about it at this point. So that was kind of trying to get the balance right as well between something kind of grotesque and something quite clinical and more like, it's really trying to get that balance.
Yeah, and absolutely. From the engineering perspective, we're often limited to like a set of like a dozen materials because these are the ones that are light and work and are machinable, right? But it's really interesting to kind of be able to venture outside of those sets of materials and say, okay, well, how does it work if we use this? It's not going to be performant, but it'll be something, and it's worth, finding that out. Yeah, it's very interesting.
Cool. I'll probably stop sharing now.
Well, cool. Thank you again for your awesome presentation. Thanks for your time.
Thank you very much.
That was a delightful note to end on, a really great example of the kind of work that goes on in the Reddit robotics community. Shows how you can come up with interesting, novel things. You can collaborate with people all around the world to build inspirational robots. So a wonderful way to end what has been a fantastic weekend. Michael, thank you very much for being with me throughout the entirety of it. Thank you very much. Thank you to the other members of the committee who have helped put this together, and thank you, of course, to everyone who applied, even those who had to drop out for various reasons. We appreciate life gets in the way. And to everyone who participated, gave a presentation, to those who dared to give a live demonstration and had the courage to put their robots on camera. And to all of the industry and the academic professionals who lent their time on a weekend to indulge us and answer our fairly basic questions and other times very novel questions. So thank you, everyone, and we'll see you, on the subreddit, in the Discord, and maybe next year for the presentation. Thank you. Have a wonderful rest of your day or evening, and that's it then. I ran out of steam for it because I've been very tired. Have a great time, everyone.
See you next year.
Cheers. See you next year.